There is a reason ancient mysteries never truly disappear. Every generation returns to the same ruins and asks the same question: what are we still missing? New tools reveal details that previous researchers could not see. New excavations uncover evidence hidden for centuries. And sometimes, a single discovery is enough to change the entire interpretation of a site. What once seemed simple becomes complicated. What appeared understood becomes uncertain again. The ancient world is full of places that refuse to stay solved. Not because they are beyond science, but because every answer reveals a deeper layer beneath it. The result is a past that continues to evolve with every discovery. A reminder that history is not just what we know, but also what we have yet to understand. Near Naples in southern Italy lies one of the most remarkable archaeological sites ever discovered, offering an unparalleled glimpse into the technological achievements of the ancient world. Buried beneath volcanic ash after the eruption of Mount Vesuvius in AD 79, the city preserved an entire urban environment in extraordinary detail. It was first systematically identified in 1748 during excavations sponsored by the Bourbon monarchy. What archaeologists uncovered was far more than the remains of a tragic disaster. Beneath the ash lay evidence of advanced engineering, sophisticated construction techniques, carefully organized urban planning, and industrial technologies whose complexity continues to challenge modern understanding. The greatest mystery is not how the city was destroyed, but how Roman engineers achieved such impressive technological capabilities. Nearly 2,000 years ago, without modern machinery, industrial manufacturing, advanced scientific instruments, or the tools of contemporary engineering. The first mystery concerns the city's vast water distribution network. Pompeii contained dozens of public fountains, private houses supplied with running water, baths, workshops, and drainage systems connected through an integrated hydraulic infrastructure. Archaeologists have identified more than 40 public fountains distributed throughout the city, many connected to pressurized pipelines fed by an aqueduct system. Water entered a large distribution structure known as the Castellum Aquae before being directed through lead pipes across the urban landscape. Modern hydraulic engineers can calculate water pressure using digital simulations, pressure gauges, and computer models. Roman engineers possessed none of these tools, yet the system successfully maintained water flow throughout a city covering approximately 66 hectares. Some researchers estimate that several million litres of water may have circulated through Pompeii's network each day. The unanswered question is how Roman engineers calculated pressure balances, flow rates, and distribution efficiency with sufficient accuracy to prevent widespread system failure. The surviving infrastructure demonstrates that they understood hydraulic principles at a level far beyond what many historians once believed. The second mystery involves the remarkable durability of Roman concrete. Pompeii contains numerous structures constructed with materials that have survived earthquakes, weathering, and nearly 2 millennia of environmental exposure. Modern concrete often begins showing significant deterioration after 50 to 100 years. By contrast, portions of Roman concrete remain structurally stable after nearly 20 centuries. Scientific studies have revealed that Roman builders used a mixture containing lime and volcanic ash known as pozzolana. Recent laboratory analyses identified mineral formations called aluminous, tobermarite, and other crystalline structures that may strengthen the material over time. Yet many aspects of the chemical process remain incompletely understood. Engineers today continue attempting to reproduce the long-term durability of Roman concrete on an industrial scale. Pompeii, therefore, preserves evidence of a material technology whose full potential may not yet be completely understood, even with modern scientific knowledge. The third mystery centers on earthquake resistance. 17 years before the eruption of Vesuvius, Pompeii experienced a major earthquake in AD 62. Ancient sources describe extensive damage throughout the region. Excavation evidence confirms that many buildings underwent repairs and reconstruction before the volcanic catastrophe. What surprises researchers is how effectively numerous structures absorbed seismic stress. Builders frequently employed flexible masonry techniques, reinforced wall junctions, multiple construction layers, and timber integration strategies that distributed mechanical forces more effectively than simple stone walls. Modern earthquake engineering relies on advanced mathematics, seismic monitoring, and structural modeling software. Roman builders had access only to observation and accumulated practical experience. Yet many of their solutions resemble principles used in contemporary earthquake-resistant architecture. Archaeologists still debate how such engineering knowledge developed and how it was transmitted across generations without formal engineering, universities, or scientific institutions. The fourth mystery concerns the thermal technologies hidden beneath the city's famous bath complexes. Pompeii contained several major public bath facilities, including the Stabian baths, Forum baths, and Central baths. These complexes relied upon a heating system known as the hypocaust. Hot air generated by furnaces circulated beneath raised floors and through hollow wall channels, creating controlled indoor temperatures. The technology effectively functioned as a form of central heating nearly 2,000 years before modern HVAC systems. Maintaining comfortable temperatures required careful regulation of airflow, fuel consumption, heat transfer, and ventilation. Engineers today use thermodynamic calculations to optimize such systems. Roman builders achieved comparable functional results through methods that remain only partially understood. Experimental archaeology has demonstrated the sophistication of hypocaust engineering, yet questions remain regarding how builders standardized designs across the Roman Empire and maintained operational efficiency over long periods. The fifth mystery involves urban planning precision. Aerial surveys reveal that Pompeii was not an unorganized collection of buildings. Streets, drainage systems, public spaces, commercial districts, and residential neighborhoods formed part of a coherent urban design. Major roads intersected according to carefully planned layouts. Infrastructure systems operated in coordination rather than isolation. Such planning required surveying techniques capable of maintaining geometric consistency across large areas. Roman surveyors used instruments such as the groma and corrobates. However, modern reconstructions suggest that achieving the observed level of accuracy would have required extraordinary technical skill. Even minor surveying errors could accumulate into major alignment problems across a growing city. The remarkable precision visible throughout Pompeii continues to fuel debate regarding the true capabilities of Roman land surveyors. The sixth mystery concerns industrial production hidden within the city. Pompeii was not merely a residential settlement. Archaeologists have identified bakeries, textile workshops, metalworking facilities, dyeing operations, food processing centers, and commercial warehouses distributed throughout the urban environment. More than 30 bakeries have been documented within the city walls. Some contained large rotary mills powered by animals, allowing flour production on a scale far exceeding household needs. Industrial equipment, production facilities, and supply chains indicate a surprisingly complex urban economy. Coordinating raw materials, labor, transportation, and distribution required sophisticated management systems. Yet, historians possess only fragmentary evidence explaining how such industrial operations were organized. The city appears to have functioned with a level of economic complexity approaching that of much later pre-industrial urban centers. The seventh mystery focuses on construction logistics. Many structures in Pompeii required enormous quantities of stone, timber, brick, mortar, and decorative materials. Transportation alone represented a major engineering challenge. Without cranes powered by engines, trucks, or modern lifting equipment, Roman builders nevertheless erected multi-story buildings, monumental temples, theatres, and public infrastructure. Archaeological evidence suggests extensive use of pulley systems, treadwheel cranes, lifting mechanisms, and specialized construction techniques. Some Roman cranes may have lifted loads exceeding 6 tons, yet relatively few physical examples survive. Most of what is known comes from artistic depictions and scattered textual references. The precise capabilities of Roman construction machinery remain a subject of ongoing research. Pompeii preserves the results of engineering achievements while leaving many questions about the machinery itself unanswered. The eighth mystery involves information networks and urban administration. Pompeii's population likely ranged between 10,000 and 20,000 inhabitants. Maintaining such a city required constant management of water supplies, waste disposal, commercial regulation, taxation, maintenance crews, and public services. Modern cities depend upon telecommunications, databases, and rapid information exchange. Pompeii relied entirely on human communication, yet the city's infrastructure functioned with remarkable effectiveness. Public notices painted on walls, standardized measurements, administrative offices, and commercial records indicate a sophisticated bureaucratic system operating beneath daily life. The mechanisms through which information moved across the city remain only partially understood, raising questions about the organizational capabilities of Roman urban governments. The Dacian fortresses of the Orăști Mountains are a network of mountain strongholds in the Carpathians of modern-day Romania. Their greatest mystery is a wall system that seems far more advanced than what would be expected in Iron Age Europe. The fortresses were known locally for centuries, but systematic archaeological investigations began during the 19th and 20th centuries. Excavations at Sarmizegetusa Regia, Costești, Blidaru, and Piatra Roșii revealed something unexpected. Instead of primitive hill forts, archaeologists uncovered a sophisticated defensive network built by the Dacians between the 1st century BC and the 1st century AD. The discoveries exposed advanced stone engineering, hydraulic systems, astronomical structures, and military architecture that continue to challenge conventional assumptions about Iron Age technology. The greatest technological mystery of the Dacian fortresses is a construction method known today as murus dasecus. At first glance, the walls appear similar to ordinary stone fortifications, but closer examination reveals a far more complex design. Each wall consisted of 2 parallel facings built from carefully cut limestone blocks. Between these outer layers, builders packed crushed stone and earth, while massive wooden beams were inserted horizontally through the structure, connecting the 2 stone faces and locking the entire system together. This created a hybrid structure, combining the compression strength of stone with the flexibility of timber. The result was extraordinary. Many surviving walls remain standing nearly 2,000 years after construction, despite earthquakes, severe winters, landslides, and centuries of abandonment. Some sections originally reached heights exceeding 10 meters and thicknesses approaching 3 meters. The mystery is not simply that the walls survived. The mystery is why they worked so well. Modern structural engineers note that purely stone walls tend to crack under repeated stress, while timber structures can flex but decay rapidly. Murus dasecus combined the advantages of both materials while reducing their weaknesses. In some respects, the concept resembles modern reinforced construction, where different materials work together to absorb forces. Yet, the Dacians developed this system without modern engineering mathematics. No written manuals survive, no architectural plans survive, and no explanation survives. Archaeologists still cannot determine exactly how Dacian builders calculated the dimensions of each wall, selected beam spacing, or predicted structural behavior under attack. Even more puzzling is the precision of the stonework. Many limestone blocks weigh between 1 and 3 tons, and some are cut with remarkable consistency. The joints fit closely enough that relatively little mortar was required. Quarry marks indicate that stones were extracted, shaped, transported, and assembled according to standardized dimensions. This raises a difficult question. How did a civilization without advanced machinery produce such uniform components on a massive scale? The problem becomes even greater when geography is considered. Most fortresses occupy elevations between 800 and 1,200 meters above sea level. The terrain consists of steep ridges, narrow valleys, and dense forests. Transporting thousands of tons of stone into these mountain positions would challenge even later medieval builders. No complete explanation exists. Researchers have proposed sled systems, wooden rollers, animal traction, and temporary road networks, yet none fully account for the scale of construction visible today. The walls become even more impressive when compared with neighbouring cultures. Many contemporary tribal societies in Europe relied primarily on earthworks, wooden palisades, or simple stone barriers. Murus Dasychus represents a level of engineering closer to major Mediterranean civilizations than to typical Iron Age hill forts. The Romans themselves encountered these fortifications during Trajan's campaigns of AD 101 to 102 and AD 105 to 106. Ancient sources describe fierce resistance. Roman engineers were among the most advanced military builders in history, constructing aqueducts, bridges, roads and fortresses throughout Europe, North Africa and the Middle East. Yet defeating the Dacian mountain strongholds required enormous military resources. That fact alone suggests the walls possessed capabilities beyond what many historians once assumed. Every fortress presents a transportation puzzle. Sarmizegetusa Regia alone required thousands of tons of limestone, andesite, timber and construction material, much of it originating from distant quarries. Moving a single 2-ton block uphill through mountainous terrain without modern cranes or vehicles would have been an enormous challenge. Moving thousands of them seems almost unbelievable. Excavations have revealed paved roads, engineered terraces, retaining walls, and transportation corridors connecting the fortresses. Some roads were carefully graded to reduce slope angles. These discoveries suggest a level of logistical planning comparable to organized states rather than isolated tribal communities. The unanswered question is how such a system was coordinated. No surviving records explain labor organization, transportation methods, or construction schedules. Within Sarmizegetusa Regia lies another enigma. Circular sanctuaries built from andesite and limestone form geometric patterns unlike anything else in Dacian Europe. The most famous structure, often called the andesite sun, consists of carefully arranged stone elements organized around a central circular platform. Researchers have proposed numerous interpretations. Some believe it functioned as a ceremonial monument, while others argue it operated as a solar calendar. A few suggest it may have combined religious and astronomical functions. Measurements indicate possible alignments with seasonal solar events, including solstices and equinoxes. Certain stone placements appear to correspond with recurring astronomical cycles. However, no consensus exists. Without written records, the true purpose remains unknown. The sanctuaries may represent one of the most sophisticated astronomical complexes north of the Mediterranean during the period. Perhaps the most surprising discoveries involve water. Archaeologists uncovered ceramic pipelines, channels, reservoirs, drainage systems, and distribution networks throughout the mountain capital. The system supplied water across difficult terrain while maintaining consistent flow. Hydraulic engineering requires accurate control of gradients. If slopes are too steep, erosion occurs. If slopes are too shallow, water stagnates. Modern calculations indicate that many sections were constructed within narrow tolerances necessary for reliable operation. How Dacian engineers achieved such precision remains unclear. No measuring instruments have been identified, and no written descriptions survive. Yet the results demonstrate practical mastery of hydraulic principles. The wealth of the Dacian kingdom was closely tied to the mineral resources of the Carpathians. Excavations have uncovered furnaces, iron tools, weapons, slag deposits, and evidence of large-scale metal production. Some workshops operated continuously for long periods, indicating specialized expertise. Roman interest in Dacia was driven in part by access to gold, silver, and iron resources. The qualities of certain Dacian weapons impressed even their enemies. Producing strong iron requires precise temperature control, airflow management, and ore selection. Many details of Dacian metallurgical practice remain poorly understood because the organic components of furnaces have largely disappeared. Archaeologists can reconstruct outcomes, but not always the exact processes that produce them. The individual fortresses are impressive. Together, they are astonishing. Sarmizegetusa Regia, Costesti Blidaru, Piatra Rosci, Bonitza, and other strongholds formed an integrated defensive system spread across the mountains. Each fortress occupied a strategic position, controlling approaches through valleys and ridges, and many locations maintained direct lines of sight with neighbouring positions. This arrangement would have enabled rapid communication using smoke, fire, or visual signals. The network resembles defensive systems more commonly associated with medieval kingdoms than Iron Age societies. Its existence implies centralized planning, resource allocation, engineering coordination, and military strategy on a remarkable scale. Question for viewers: was Murus Dasychus an independent Dacian invention, or was it based on engineering knowledge that has completely vanished from history? Vrelo-Sharkamen is a late Roman imperial complex in eastern Serbia that holds one of the ancient world's most underrated engineering mysteries. How were Roman engineers able to construct a royal burial site with remarkable precision in a remote mountainous area, and why do some of the sophisticated technologies used there remain only partly understood today? The story of Vrelo-Sharkamen entered modern archaeology during systematic excavations conducted in eastern Serbia during the late 20th century. Archaeologists uncovered the remains of a fortified imperial residence, ceremonial buildings, defensive walls, and one of the most remarkable royal mausoleums ever discovered in the Balkans. Evidence suggests that the complex was associated with Emperor Maximinus Daia, one of the rulers of the Roman Tetrarchy during the early 4th century AD. Yet, despite decades of study, many aspects of the site's construction, logistics, and funerary technologies continue to raise difficult questions. The first mystery involves location. Roman imperial residences were normally built near major cities, military centers, or strategic transportation routes. Vrelo-Sharkamen stands apart. The complex occupies a relatively isolated area surrounded by rugged terrain in eastern Serbia. Constructing an imperial complex in such a location required enormous logistical coordination. Archaeological surveys indicate that the fortified enclosure covered more than 3 hectares and contained numerous monumental structures. Thousands of tons of stone, brick, timber, lime, and roofing materials had to be transported across difficult terrain. Modern engineers understand the materials used, but the organization behind the project remains difficult to reconstruct. No large-scale industrial staging areas have yet been identified nearby. No complete transportation network serving the site has been discovered. Yet, the finished complex displays the characteristics of a carefully planned imperial project. Similar logistical achievements can be seen at the Palace of Felix Romuliana, approximately 40 kilometers away, another imperial residence connected to the Tetrarchic period. The comparison suggests that Roman authorities possessed a regional construction system capable of mobilizing labor and resources on a scale far greater than many historians once believed. The second mystery concerns surveying and architectural precision. Excavations reveal carefully aligned walls, organized courtyards, defensive structures, and ceremonial spaces constructed according to a unified architectural plan. Roman engineers are known to have used instruments such as the groma for alignment and the corrobates for leveling. However, maintaining geometric consistency across an entire complex built on uneven terrain required remarkable technical skill. Archaeological measurements show that many structures follow consistent orientations despite variations in topography. Similar precision can be observed in imperial complexes throughout the Roman world, yet Vrelo-Sharkamen presents a challenge because of its location. Modern surveyors working in mountainous terrain rely on advanced optical equipment, satellite positioning systems, and digital mapping technologies. Roman engineers achieved impressive accuracy without any of these tools. Exactly how they coordinated large-scale construction in such conditions remains only partially understood. The third mystery involves water management. Every Roman palace depended upon reliable access to water. Baths, kitchens, fountains, workshops, and residential quarters required constant supply. Archaeologists have identified evidence for hydraulic infrastructure at Vrelo-Sharkamen, including channels and water-related installations. However, the full system has never been completely reconstructed. This raises an important engineering question. A royal complex housing elites, servants, guards, and ceremonial functions would have required substantial quantities of water every day. Even modest Roman bath facilities could consume thousands of litres daily, yet the precise source capable of sustaining long-term operation remains uncertain. Some researchers suspect that portions of the hydraulic network remain buried beneath later deposits or outside the currently excavated area. Others propose that natural springs in the region were exploited more efficiently than previously assumed. Until additional evidence emerges, the true scale of the water system remains one of the site's unresolved technological puzzles. The fourth and perhaps most fascinating mystery centers on the royal mausoleum and the technology of cremation. This discovery transformed Sharkamen from an interesting imperial residence into one of the most significant archaeological sites in southeastern Europe. Archaeologists uncovered a monumental funerary complex containing cremated human remains and an extraordinary collection of gold jewelry. The treasure included necklaces, earrings, rings, pendants, and luxurious ornaments crafted with astonishing precision. Analysis of the artifacts revealed workmanship of exceptional quality, consistent with elite imperial production during the late Roman period. The cremation itself presents several unanswered questions. Roman cremation was not a simple process. To completely reduce a human body to calcined bone required temperatures that could exceed 800 degrees Celsius. Achieving and maintaining such temperatures demanded careful control of fuel, airflow, combustion chambers, and pyre construction. Experimental archaeology has demonstrated that successful cremation requires a highly organized sequence of operations and considerable technical knowledge. At Vrelo-Sharkamen, the remains indicate a cremation ceremony conducted with extraordinary sophistication. The bones were carefully collected after burning and deposited within a monumental funerary setting. This suggests not merely ritual activity, but a controlled technological process. Some researchers have compared the operation to high-temperature industrial procedures because maintaining consistent combustion over extended periods is remarkably difficult without extensive experience. The gold artifacts introduce an even deeper mystery. Several objects exhibit extremely fine decorative techniques involving tiny granules and delicate wire elements. Some gold wires measure fractions of a millimeter in thickness. Creating such features required advanced metallurgical knowledge, specialized tools, and highly skilled craftsmen. Modern microscopic analysis shows that Roman goldsmiths employed techniques including granulation, filigree, soldering, and alloy control. Yet, historians continue to debate the exact procedures used to join microscopic components without damaging surrounding structures. Even today, reproducing some ancient jewelry techniques requires laboratory conditions and highly trained specialists. The comparison becomes even more remarkable when viewed alongside other famous treasures of the Roman world. Many pieces discovered at Vrelo-Sharkamen rival the quality of jewelry recovered from imperial contexts in Italy, Egypt, and Asia Minor. The existence of such craftsmanship in a relatively remote Balkan locations suggests access to artisans connected to elite imperial workshops. Another unanswered question concerns the identity of the individual buried there. many scholars believe the mausoleum may have belonged to a female member of the imperial family associated with Maximinus Dia. The richness of the grave goods supports this interpretation, yet definitive proof remains elusive. The result is a rare combination of historical, technological and archaeological uncertainties centered on one of the most important funerary discoveries in the Balkans. The fifth mystery involves the speed of construction. Historical evidence indicates that the complex was likely built during a relatively brief period connected to the Tetrarchic era. This means planners had to coordinate architects, engineers, masons, metalworkers, labourers, and supply networks within a limited time frame. The Roman Empire certainly possessed immense resources. However, transforming a remote landscape into a fortified imperial centre required extraordinary administrative efficiency. Archaeologists can study the finished structures, but much of the organisational system responsible for creating them has disappeared. The workers, engineers and managers who made the project possible remain largely invisible in the archaeological record. The final mystery concerns abandonment. Despite its apparent importance, Vrelo-Sharkamen did not continue functioning as a major imperial centre for centuries. Political instability, dynastic change, shifting military priorities, and broader transformations within the Roman Empire may all have contributed to its decline. Yet the exact sequence remains uncertain. Which mystery of Vrelo-Sharkamen fascinates you the most? Let us know your theory in the comments below. Bojnar Valley is a fortified early medieval settlement in western Slovakia that preserves one of the most overlooked technological mysteries of early Europe. Hidden within its massive earthworks are clues suggesting that a society living more than 1,100 years ago possessed engineering, metallurgical, and organizational capabilities far more sophisticated than historians once believed. The greatest mystery is not that Bojnar Valley existed. The real mystery is how a regional power with no written technical manuals, no industrial machinery, and limited resources managed to construct enormous fortifications, operate large-scale metal production, and maintain a level of technical standardization that still raises questions today. Bojnar Valley lies in the Považský Inovex mountains of western Slovakia, approximately 80 kilometers northeast of Bratislava. Archaeological investigations intensified during the 20th and 21st centuries, revealing one of the largest fortified centres associated with the Great Moravian cultural sphere. What initially appeared to be a typical hill fort soon emerged as something much more significant, as excavations uncovered extensive defensive systems, workshops, weapons, tools, religious artefacts, and evidence of specialized production on a scale rarely associated with Central Europe during the 9th century. Radiocarbon dating, artifact analysis, and dendrochronological studies indicate that the site reached its peak between the late 8th and early 10th centuries. During this period, Bojnar Valley functioned as a major political, military, and economic centre. Yet, despite decades of research, many of its most impressive technological achievements remain only partially understood. The first mystery concerns the enormous defensive structures surrounding the settlement. Archaeologists have identified extensive ramparts constructed from earth, timber, and stone, with some sections reaching widths exceeding 10 meters, while the overall defensive perimeter stretched for several kilometers. Building fortifications of this scale required a level of planning comparable to major military projects elsewhere in Europe. Researchers estimate that thousands of mature trees would have been harvested, transported, shaped, and incorporated into the defensive walls, and every stage demanded coordinated labour, logistical planning, and engineering knowledge. What makes the system particularly remarkable is its structural design. Rather than relying on simple earth embankments, the builders created complex timber frameworks filled with soil and stone. Modern engineers note that such designs distribute pressure efficiently and reduce the risk of catastrophic collapse. Similar principles appear in some Carolingian fortifications and Scandinavian defensive works. Yet Boyna Valley demonstrates an unusually sophisticated implementation. The unanswered question is how such knowledge was acquired and transmitted. No contemporary documents describe the construction techniques, and the builders left behind the structures themselves, but not the technical instructions needed to reproduce them. The most fascinating technological mystery at Boyna Valley involves metallurgy. Excavations have produced extraordinary quantities of iron artifacts, including weapons, agricultural tools, construction hardware, knives, axes, spearheads, horseshoes, and manufacturing waste. The sheer volume suggests that Boyna Valley was not merely consuming metal products, it was producing them on a large scale. This creates a major archaeological puzzle. Iron production in the 9th century was far more complicated than many people imagine. Bloomery furnaces typically operated at temperatures between 1100 and 1300 degrees Celsius, and achieving and maintaining such temperatures required carefully designed furnaces, high-quality charcoal, controlled airflow, and experienced craftsmen. Even minor errors could ruin an entire batch of metal. To understand the challenge, consider that producing only 1 kilogram of workable iron often required several kilograms of ore and many more kilograms of charcoal. Large-scale production therefore demanded enormous quantities of raw materials and a reliable supply chain. Forest resources had to be managed, ore sources had to be identified and exploited, and transportation systems had to move materials continuously between extraction sites and workshops. Archaeologists have discovered evidence of slag, furnace remains, and metalworking debris, confirming industrial-level activity for its time. However, the complete production infrastructure has never been fully reconstructed, and many of the furnaces have disappeared, leaving only fragments behind. This raises several unanswered questions. How many furnaces operated simultaneously? How was airflow regulated without advanced mechanical devices? How were temperatures monitored in an age without thermometers? How did craftsmen maintain consistent quality across hundreds or perhaps thousands of finished products? Modern experimental archaeology has demonstrated that bloomery iron production requires highly specialized knowledge accumulated through years of experience. Yet the craftsmen of Boyna Valley achieved output levels suggesting organized production rather than occasional local manufacturing. Comparisons with contemporary sites reveal the significance of the mystery. Many settlements across Central Europe contain evidence of ironworking, but few display the concentration of metal artifacts found at Boyna Valley. Some researchers believe the site may have functioned as a regional production center supplying weapons and tools across a large territory associated with Great Moravian power. If true, Boyna Valley would represent something approaching an early industrial complex centuries before the emergence of mechanized manufacturing. Another intriguing puzzle involves the remarkable consistency of many recovered iron objects. Measurements of weapons and tools show patterns suggesting standardization. Numerous spearheads, knives, and metal fittings exhibit similar proportions and manufacturing techniques, and such uniformity implies organized production methods rather than isolated craftsmanship. Today, standardization is associated with factories, gauges, templates, and quality control systems, yet 9th century craftsmen possessed none of these technologies in their modern form. The existence of consistent products suggests that artisans may have used templates, measurement traditions, or apprenticeship systems capable of maintaining production standards across generations. Although archaeologists still debate how such consistency was achieved, the mystery becomes even more significant when viewed in a military context. Standardized weapons simplify training, repairs, logistics, and battlefield organization. If Boyna Valley was producing military equipment according to common specifications, it would indicate a surprisingly advanced level of administrative control. Boyna Valley was not isolated. Artifacts discovered at the site reveal connections extending across Central Europe. Imported goods, religious objects, and stylistic influences demonstrate participation in broader economic and political networks. Maintaining such connections required reliable communication systems and transportation routes. Messages, materials, and personnel had to move across forests, rivers, and mountainous terrain. Unlike the Roman Empire, however, Great Moravian society did not possess a vast network of paved roads. The logistical challenge remains difficult to explain. Large fortifications, metal workshops, and military forces all depended on regular deliveries of food, fuel, raw materials, and labour, yet the mechanisms that supported this system remain largely invisible in the archaeological record. Among the most famous discoveries at Boynar Valley are gilded bronze plaques depicting Christian motifs. These artifacts rank among the earliest known Christian objects discovered in Slovakia. Their craftsmanship is extraordinary. The plaques feature detailed iconography, precise casting techniques, and sophisticated decorative work. Producing such objects required knowledge of metallurgy, mold preparation, finishing techniques, and precious metal application. Some scholars argue that the plaques were imported from advanced artistic centres connected to the Carolingian world, while others suggest local production by highly skilled craftsmen. If they were produced locally, the implications are profound. It would mean that Boynar Valley possessed artisans capable of working at a level comparable to some of the finest workshops in contemporary Europe. The true origin of these objects remains uncertain. What do you think was the most advanced technology hidden inside Boynar Valley? The massive fortifications, the standardized weapons, or the large-scale iron production system? Migvimevi Monastery is a medieval monastic complex carved into the limestone cliffs of western Georgia. Perched above the Farila River Valley near the town of Kiachura, it appears at first glance to be just another remote mountain monastery. Yet hidden within its caves and stone walls lies a collection of engineering mysteries that continue to challenge archaeologists, architects, geologists, and conservation scientists. The greatest mystery is not why the monastery was built in such an inaccessible location. The real mystery is how medieval builders managed to transform a dangerous cliffside cave system into a stable religious complex that has survived more than 7 centuries of earthquakes, erosion, humidity, and environmental change. The story of Mugvimevi entered modern scholarship through archaeological and historical investigations conducted during the 19th and 20th centuries. Located in the Imereti region of Georgia, the monastery was known locally for centuries, but systematic studies revealed that much of the complex had been integrated directly into natural limestone formations. What researchers initially believed to be a simple cave monastery turned out to be a sophisticated combination of natural geology and engineered architecture. The first mystery concerns construction itself. The monastery was built against a steep limestone cliff that rises dramatically above the valley floor. Even today, transporting construction materials to the site requires considerable effort. During the 13th century, builders had no cranes, trucks, powered lifting equipment, or modern scaffolding systems, yet they successfully moved thousands of kilograms of stone, timber, roofing materials, plaster, pigments, and water to elevations that remained challenging even for modern workers. This problem becomes more puzzling when compared with other famous cliffside religious complexes. The cave monasteries of Cappadocia in Turkey were largely excavated from relatively soft volcanic tuff. The monasteries of Meteora in Greece were supplied using ropes and baskets suspended from towering sandstone pillars. Mugvimevi, however, occupies a narrow limestone environment that combines the difficulties of both systems. Archaeologists can observe the finished result, but the exact logistics network used by medieval builders remains unknown. No contemporary engineering records survive to explain how construction materials were transported and assembled with such precision. The second mystery involves geological engineering. Natural caves rarely possess the shape required for permanent human occupation. Most contain unstable ceilings, irregular chambers, and unpredictable fracture networks. Yet the spaces incorporated into Migvimevi demonstrate evidence of deliberate modification. Builders expanded chambers, reshaped passages, and integrated architectural features into existing rock formations without triggering catastrophic collapse. Modern engineers rely on computer simulations, geological surveys, laser mapping, and structural analysis to evaluate the stability of excavated spaces. Medieval builders possessed none of these tools. Nevertheless, the monastery has remained standing for more than 700 years. This suggests an empirical understanding of rock mechanics that was far more sophisticated than historians once assumed. Some chambers appear to have been expanded within meters of natural fracture zones, yet they remain remarkably stable. Researchers still cannot fully explain how builders identified which sections of limestone could be safely removed and which had to remain untouched. The third mystery concerns seismic survival. Georgia lies within a tectonically active region, influenced by the collision between the Arabian and Eurasian plates. Historical records document numerous earthquakes throughout the Caucasus. Many medieval structures across the region suffered severe damage or complete destruction. Migvimevi survived. Architectural studies suggest that the monastery benefits from an unusual relationship between built structures and natural rock. Instead of functioning as a completely independent building, parts of the monastery behave almost like extensions of the cliff itself. Some walls appear to distribute stress into the surrounding limestone rather than resisting seismic forces alone. This hybrid natural-artificial structure may have created a primitive form of earthquake resistance. Whether this effect was intentionally engineered or accidentally discovered remains unknown. The fourth mystery involves environmental control. Cave environments are notoriously difficult places to preserve organic materials. Humidity fluctuations, condensation, mineral deposits, biological growth, and temperature changes normally destroy fragile surfaces over time. Yet Migvimevi has maintained stable interior conditions for centuries. Measurements from comparable limestone cave systems indicate that underground temperatures often remain within a narrow range throughout the year, sometimes varying by only a few degrees Celsius, despite extreme seasonal changes outside. Researchers suspect that natural ventilation channels within the cliff may create a self-regulating airflow system. These hidden pathways could remove excess moisture while maintaining stable temperatures. However, the complete ventilation network has never been fully mapped. The cave may contain environmental mechanisms that are still poorly understood. The fifth mystery concerns architectural precision. Religious architecture in the Orthodox Christian tradition follows highly structured spatial principles. Churches are normally aligned according to symbolic orientations and geometric relationships. Constructing such spaces inside irregular caves presents enormous challenges. Despite the limitations imposed by natural rock formations, the main church at Migvimevi exhibits surprisingly consistent proportions. Wall alignments, ceiling transitions, and liturgical spaces demonstrate planning that appears incompatible with the constraints of the surrounding geology. Achieving such accuracy without modern surveying instruments would have required exceptional technical skill. The methods used by medieval builders to establish geometric control inside a complex cave environment remain largely speculative. The sixth mystery involves hidden passages and unexplored spaces. Archaeologists have identified secondary chambers, narrow corridors, and inaccessible recesses throughout the monastery complex. Some may have served as storage areas, refuges, workshops, or monastic cells, while others remain unexplored. Despite advances in ground-penetrating radar and 3D mapping, large parts of the Migvimevi cave system remain difficult to study because of structural and conservation concerns. As a result, researchers still cannot fully understand how the monastery functioned at its peak. The seventh and perhaps greatest mystery concerns the preservation of the monastery's medieval frescoes. This mystery has attracted increasing attention from conservation scientists because the survival of these paintings appears almost improbable. The frescoes have endured for centuries despite exposure to environmental conditions that normally destroy wall paintings. Humidity, airborne particles, mineral salts, microorganisms, and temperature fluctuations represent constant threats to painted surfaces. In many medieval sites across Europe and the Near East, frescoes have faded dramatically or disappeared entirely, yet significant portions of the artwork at Migvimevi remain visible. The science behind fresco preservation is extremely complex. Traditional frescoes are created by applying mineral pigments onto wet lime plaster. As the plaster cures, calcium hydroxide reacts with carbon dioxide from the atmosphere to form calcium carbonate. This process locks pigments into the wall itself, creating extraordinary durability. However, successful preservation requires stable environmental conditions. Excess moisture can dissolve salts. Drying cycles can produce cracking. Biological growth can destroy pigment layers. Researchers studying comparable medieval frescoes have found that even small fluctuations in relative humidity can accelerate deterioration. In some heritage sites, annual restoration efforts are required simply to slow the damage. The fact that Migvimevi's paintings survived for centuries raises a remarkable question. Did medieval craftsmen possess specialized knowledge of materials that modern science still does not fully understand? Microscopic analyses of medieval plasters from various Georgian monuments have revealed carefully selected mixtures of lime, sand, mineral aggregates, and local additives. Some formulations exhibit exceptional resistance to moisture penetration. Others demonstrate unusual mechanical stability. It is possible that the artisans responsible for Migvimevi employed regional techniques optimized through generations of experimentation. Even more intriguing is the possibility that the cave itself participates in preservation. Natural limestone acts as a chemical buffer, helping regulate humidity and atmospheric chemistry. The cave environment may continuously stabilize conditions around the frescoes. If true, the paintings represent not merely an artistic achievement, but part of a larger environmental engineering system, created through the interaction of geology, architecture, and material science. Modern conservation laboratories can analyze pigment composition, plaster structure, mineral content, and microclimatic conditions. Yet no single explanation fully accounts for the remarkable state of preservation observed in parts of the monastery. The survival of the frescoes appears to result from a combination of factors so complex that researchers are still attempting to separate them centuries later. Mediana is a Roman imperial estate near Niš in modern-day Serbia that preserves one of the most overlooked technological mysteries of the ancient world. How did Roman engineers and artisans achieve extraordinary geometric precision, material durability, and environmental control without modern scientific instruments? Mediana lies approximately 5 kilometers east of Niš, the birthplace of Emperor Constantine the Great. Archaeological investigations began in the 20th century, but large-scale excavations accelerated after World War II and continue today. Beneath layers of soil, researchers uncovered an enormous imperial complex covering several hectares, including villas, bathhouses, water systems, workshops, storage facilities, and some of the finest Roman mosaics ever discovered in the Balkans. What initially appeared to be another luxurious Roman residence soon revealed a collection of engineering achievements that continue to puzzle archaeologists, architects, and materials scientists. One of the first mysteries discovered at Mediana was hidden beneath the floors. Excavations revealed an extensive hypercourse system, the Roman equivalent of central heating. Hundreds of small brick pillars supported floors, while hot air generated by furnaces circulated underneath rooms and through hollow wall channels. The technology itself is not unique, as similar systems existed throughout the Roman Empire. What makes Mediana remarkable is its scale and apparent efficiency. Modern thermal simulations suggest that maintaining relatively stable temperatures across large residential spaces requires careful management of airflow, pressure, and heat distribution. Yet Roman builders achieved this without thermometers, modern fluid dynamics, or mechanical control systems. Some heated rooms exceeded 100 square meters in area, requiring hot air to travel through networks of channels while avoiding excessive temperature variations. Even today, uneven heating remains a challenge in many modern buildings. Researchers continue to debate how Roman engineers optimized these systems. Was the knowledge based on empirical experimentation accumulated over centuries, or did Roman architects possess practical engineering methods that have not survived in written records? The mystery becomes even more intriguing when compared with medieval Europe. After the collapse of the Western Roman Empire, many large-scale heating technologies disappeared for centuries. In some regions, buildings would not achieve comparable indoor heating systems until more than 1,000 years later. Another puzzle concerns the remarkable durability of Mediana's construction materials. Many walls, foundations, and floors survived nearly 700 years despite earthquakes, seasonal freezing, groundwater exposure, warfare, and abandonment. Laboratory analyses reveal mixtures of lime mortar, crushed brick, sand, and local aggregates. However, scientists still debate why some Roman mortars continue to outperform certain modern materials under long-term environmental stress. Microscopic examinations show evidence of complex chemical interactions occurring over centuries. Some Roman mortars appear capable of partially sealing microcracks through ongoing mineral growth. Similar phenomena have been documented in other Roman sites, but the exact recipes often varied regionally. The challenge is that ancient builders left no detailed manufacturing manuals explaining precise proportions. Archaeologists can identify ingredients, but reconstructing exact production methods remains difficult. How did Roman craftsmen consistently produce materials capable of surviving almost 2 millennia when many modern structures require major repairs after only a few decades? The greatest technological mystery of Mediana lies not beneath the floors but on top of them. The site contains some of the most sophisticated geometric mosaics in the Roman world. Thousands upon thousands of tiny tesserae, many only a few millimeters across, were arranged into complex patterns exhibiting extraordinary symmetry, alignment, and mathematical consistency. At first glance, the mosaics appear decorative. Under closer examination, they become an engineering puzzle. Several floors contain circles, polygons, interlocking patterns, and repeating geometric sequences that maintain accuracy across large surfaces. In some sections, measurement studies reveal deviations of only a few millimeters despite spanning several meters. Achieving such precision is difficult even with modern tools. Consider a simple circle. If a circle with a diameter of 10 meters deviates by just 1%, the error becomes immediately visible. Yet many Mediana mosaics maintain proportions that appear astonishingly accurate despite being assembled entirely by hand. The challenge becomes even greater when considering the construction processes. Mosaic artisans first prepared multiple foundation layers, then transferred designs onto large surfaces and installed thousands of individual stone pieces while maintaining geometric relationships across the entire composition. No laser levels existed, no digital drafting software existed, and no precision manufactured rulers existed. And yet the final results often rival geometric layouts produced centuries later. Some scholars propose that Roman craftsmen employed sophisticated grid systems using ropes, measuring rods, compasses, and proportional geometry. Others suggest the existence of highly standardized workshop methods passed through generations of specialists. The mystery is not that Romans understood geometry. Euclid's geometric principles had existed for centuries. The mystery is how these abstract mathematical concepts were translated into physical reality with such extraordinary consistency. Comparisons with medieval mosaics reveal an important difference. While medieval artists produced magnificent works, many Roman mosaics demonstrate a level of geometric regularity that is surprisingly difficult to replicate manually. Modern experimental archaeologists attempting to reproduce Roman mosaic techniques often discover that maintaining precise symmetry across large surfaces requires immense planning, coordination, and skill. Even minor measurement errors accumulate rapidly. A deviation of only 1 millimeter repeated thousands of times can distort an entire design. Yet many Mediana mosaics show little evidence of cumulative error. How were these artisans trained? How were measurements transferred so accurately? And why did some of these texts seemingly disappear after the fall of Rome? These questions remain among the most fascinating unsolved technological puzzles associated with the site. Water was essential to Mediana's operation. Archaeologists uncovered pools, fountains, baths, channels, reservoirs, and drainage systems integrated into a single hydraulic network. Maintaining water flow across such a complex environment required precise control of gradients. Modern engineers understand that even slight errors in slope can cause serious problems. Too little gradient results in stagnation, while too much creates erosion and structural damage. The Romans lacked modern surveying instruments, yet their water systems frequently achieved remarkable efficiency. At Mediana, the hydraulic infrastructure appears carefully coordinated with residential, ceremonial, and agricultural functions. Water distribution was not random, it was engineered. Researchers continue to investigate how Roman surveyors achieved such accuracy using only manual tools and practical experience. The scale of Mediana raises a key question: who built it? The complex required vast amounts of materials and a large workforce of architects, engineers, craftsmen, labourers, and administrators. Although Constantine's era lacked modern planning tools, Mediana's water, heating, architectural and decorative systems worked together seamlessly. This level of coordination suggests advanced planning methods that remain largely unknown today. Fort La Prée is a coastal fortress on the French island of Île de Ré that preserves one of the most overlooked engineering mysteries of early modern military history. Built between 1625 and 1630, on the edge of the Atlantic Ocean, the fortress was designed to withstand artillery bombardment, saltwater corrosion, unstable coastal ground, and centuries of violent storms. Nearly 400 years later, much of the original structure still survives. The mystery is not simply how the fortress remained standing. The real mystery is how 17th century engineers achieved such extraordinary geometric precision, structural durability, and defensive efficiency without modern surveying equipment, reinforced concrete, computer modelling, or industrial machinery. The story of Fort La Prée begins on the western coast of France on Île de Ré, an island strategically positioned near the important Atlantic port of La Rochelle. Historians have long known about the fortress, but detailed architectural surveys conducted during restoration projects in the 20th and 21st centuries revealed unexpected levels of engineering sophistication hidden within its walls. Laser scanning, structural analysis, and archaeological studies showed that many parts of the fortress were built with a precision that continues to surprise military historians and engineers. One of the first mysteries concerns the fortress' survival against one of the most destructive environments on Earth. Modern coastal engineers recognize that seawater is extremely damaging to stone structures. Salt crystals penetrate pores within masonry, expand during moisture cycles, and gradually fracture building materials from within. Studies conducted on Atlantic coastal structures show that marine weathering can destroy exposed stone within a few centuries if construction methods are inadequate. Yet Fort La Prée has remained standing for nearly 400 years, despite constant exposure to ocean winds, humidity, and salt spray. The question is simple: how did 17th century builders create masonry capable of surviving conditions that challenge even modern structures? Researchers examining historical mortars discovered sophisticated mixtures of lime, aggregates, and carefully selected local materials. Some sections of the fortress display unusual resistance to deterioration compared with contemporary coastal structures. Laboratory analyses suggest that long-term chemical reactions within the mortar may have strengthened the material over time. Similar phenomena have been observed in Roman marine concrete, which continues to puzzle scientists because it sometimes becomes stronger after centuries of exposure to seawater. Although Fort La Prée does not use Roman concrete technology, the comparison raises an intriguing possibility that early engineers has possessed practical knowledge of durable construction techniques that are only partially understood today. Another mystery involves the foundations. The fortress was constructed on relatively unstable coastal terrain where heavy masonry structures would normally face settlement problems. Modern engineers solve such challenges using soil surveys, geotechnical drilling, computer simulations, and advanced foundation systems. None of these technologies existed in the 17th century, yet the builders successfully supported thousands of tons of stone walls, bastions, gun platforms, and defensive structures. Surveys indicate that the foundations extend farther and distribute loads more effectively than many historians originally expected. The precise methods used to evaluate ground stability remain largely undocumented. Some historians believe military engineers developed empirical techniques through generations of experience constructing fortifications across Europe. However, the absence of detailed technical records means that the exact calculations and procedures remain uncertain. The third mystery involves the fortress's drainage system. Water is one of the greatest enemies of military architecture. Rainwater trapped within walls can weaken mortar, destabilize foundations, and accelerate structural decay. Engineers at Fort La Prée incorporated hidden drainage channels beneath courtyards and within defensive structures to remove excess water efficiently. Modern laser surveys reveal that these channels maintain remarkably consistent gradients. Even slight errors in slope could have caused standing water and long-term damage. Achieving such precision today would be straightforward with laser levels and electronic instruments. The builders of Fort La Prée relied entirely on manual measurements, ropes, wooden instruments, and geometry. The accuracy they achieved remains impressive even by modern standards. The fourth mystery concerns logistics. Fort La Prée required enormous quantities of stone, timber, lime, and metal. Historians estimate that major 17th century fortifications often involved moving thousands of tons of materials over difficult terrain. The challenge becomes even greater on an island separated from the mainland by strong tides and unpredictable Atlantic weather. Without steam engines, cranes, trucks, or mechanized lifting equipment, workers transported and positioned massive building materials with remarkable efficiency. Historical records document the construction effort, but provide limited information about the specific techniques used to lift, align, and place heavy stones. Similar questions surround many large historical engineering projects. The builders clearly possessed practical solutions, yet much of that technical knowledge was never fully recorded. The greatest mystery of Fort La Prée, however, involves the astonishing geometric precision of its bastion design. This mystery lies at the heart of the fortress. Unlike medieval castles, which relied on high vertical walls, Fort La Prée belongs to a new generation of military architecture developed in response to gunpowder artillery. Cannons had transformed warfare. Tall castle walls became vulnerable targets. Military engineers responded by creating low-profile fortresses with angled bastions capable of resisting bombardment while providing overlapping fields of fire. The effectiveness of such fortifications depended entirely on geometry. Every wall angle, every bastion projection, and every defensive line had to be positioned with extraordinary accuracy. A small error could create a blind spot where attackers could approach without being exposed to defensive fire. A miscalculated angle could weaken the entire defensive system. Modern military architects use computer simulations to model lines of sight and ballistic coverage. 17th century engineers possessed none of these tools. Yet when modern researchers analysed surviving bastion fortifications throughout Europe, including Fort La Prée, they discovered geometric layouts that closely match sophisticated mathematical principles. The bastions at Fort La Prée were designed so that defenders positioned on one wall could protect adjacent walls with crossfire. This created overlapping defensive zones that minimized vulnerable areas. The concept appears straightforward today, but implementing it across an entire fortress required extensive geometric planning. Laser mapping has revealed that many angles remain remarkably consistent despite centuries of repairs and environmental damage. In some sections, deviations are measured in only fractions of a degree. Such precision raises a difficult question. How did engineers achieve this level of geometric accuracy without modern instruments? One possible answer lies in advanced surveying methods inherited from Renaissance military science. European engineers of the 16th and 17th centuries increasingly applied geometry, trigonometry, and mathematical planning to fortress construction. However, surviving documents rarely provide enough detail to reconstruct the complete process. The challenge becomes even more impressive when scale is considered. Maintaining geometric precision across a fortress, measuring hundreds of meters, requires controlling cumulative errors. Modern surveyors use total stations, GPS systems, and digital mapping tools because small mistakes can multiply rapidly over distance. Engineers at Fort La Prée achieved comparable results using simple optical devices, measuring chains, compasses, and mathematical calculations performed entirely by hand. Comparisons with other famous bastion fortresses reveal similar mysteries. The star forts, designed by engineers such as Sébastien Leprest de Vauban, later demonstrated extraordinary geometric sophistication across Europe. Some fortresses covered dozens of hectares while maintaining carefully calculated defensive relationships between every wall and bastion. Fort La Prée represents an earlier stage in this evolution, making its precision even more remarkable. Perhaps the most fascinating aspect is that the fortress geometry was not merely theoretical. It functioned in real combat conditions. Defensive systems depended on precise lines of fire, visibility, communication, and artillery placement. Any significant geometric errors would have been exposed immediately during military engagements. The fortress therefore serves as a full-scale demonstration of engineering knowledge that worked in practice rather than merely on paper. Was the geometric precision of Fort La Prée the result of mathematical genius, lost surveying techniques, or engineering knowledge that modern history has underestimated? Necropolis of the Via Triumphalis is a Roman burial city hidden beneath Vatican City, Italy. Its tombs have survived underground for nearly 2,000 years, preserving colours, engineering, and construction techniques that continue to challenge modern archaeologists. The necropolis was discovered during archaeological investigations beneath Vatican territory in the 20th century, with major excavations expanding during the late 20th and early 21st centuries. Buried along the ancient Via Triumphalis, a road once used by victorious Roman generals, the site revealed dozens of tombs, funerary monuments, inscriptions, mosaics, and painted chambers preserved beneath layers of earth that protected them from centuries of urban development. At first glance, the necropolis of the Via Triumphalis appears to be another Roman cemetery. Yet archaeologists quickly realized they were looking at something far more complex. The site contains streets, family tombs, communal burial structures, workshops, decorative programs, and architectural elements arranged with remarkable organization. Rather than a random collection of graves, it resembles a carefully planned underground city. The first mystery is how Roman engineers managed to create a long-lasting funerary landscape in an environment that should have destroyed it. Underground structures face constant threats from moisture, ground pressure, microbial activity, and chemical erosion. Modern underground facilities often require continuous maintenance. Yet parts of this necropolis remained intact for nearly 2,000 years. Researchers estimate that some burial chambers survived beneath several meters of soil while maintaining structural stability, despite centuries of natural ground movement. The engineering principles responsible for this durability remain only partially understood. One of the most intriguing questions concerns Roman knowledge of underground construction. Today, engineers use geological surveys, computer simulations, and advanced instrumentation to predict soil behavior. Roman builders possessed none of these technologies, yet many tombs were constructed with foundations adapted to varying soil conditions. Walls remain surprisingly vertical, vaults remain standing, and many structures show little evidence of catastrophic collapse. The challenge becomes even more remarkable when compared with other ancient civilizations. Many underground burial complexes in the ancient Mediterranean suffered severe structural deterioration over time. Portions of the Egyptian necropolis at Saqqara required extensive stabilization. Numerous Hellenistic tombs experienced significant deformation due to soil pressure. In contrast, many chambers within the Via Triumphalis necropolis retain their original geometry. Archaeologists suspect Roman engineers possessed practical knowledge of soil mechanics, gained through centuries of infrastructure construction. Across the empire, they built roads, aqueducts, bridges, tunnels, and mines. The necropolis may preserve evidence of engineering traditions that were never fully documented in surviving texts. Another mystery lies within the construction materials themselves. Laboratory analysis has revealed the use of lime-based mortars, similar to those found in Roman harbours, baths, and monumental architecture. Some mortars exhibit extraordinary cohesion despite nearly 2 millennia of exposure to moisture. Modern Portland cement typically begins showing significant deterioration after decades of environmental stress. Roman mortars in some locations have survived 20 centuries. Scientists studying Roman construction materials discovered microscopic mineral formations that appear to strengthen structures over time. Tiny crystalline growths develop within cracks, effectively creating a form of natural self-repair. Recent research on Roman concrete from other sites demonstrated that lime clasts within the material may contribute to long-term durability. However, the precise methods used by Roman builders remain uncertain. Ancient authors, such as Vitruvius, described construction techniques, but their accounts do not fully explain why certain Roman materials outperform many modern equivalents. The Via Triumphalis necropolis provides another example of this technological puzzle. Perhaps the greatest mystery of the entire necropolis involves colour. Visitors entering some burial chambers encounter painted walls whose pigments remain visible after nearly 2,000 years. Reds, yellows, blacks, and traces of other colours continue to survive, despite conditions that should have erased them long ago. This preservation presents a major scientific puzzle. Colour is among the most fragile elements of ancient architecture. Exposure to moisture, salt crystallization, temperature fluctuations, fungi, bacteria, and oxidation normally destroys painted surfaces. Even many medieval frescoes, only a few centuries old, have suffered extensive fading. Yet pigments within portions of the Via Triumphalis necropolis endured for approximately 20 centuries. To understand the scale of this achievement, consider a comparison. Modern exterior paints often require replacement after 10 to 20 years depending on environmental conditions. Some industrial coatings begin degrading within a few decades. Roman pigments at the necropolis have survived 100 times longer. Scientific analyses indicate that Roman artists relied heavily on mineral-based pigments. Red colours often originated from iron oxide compounds. Yellow pigments frequently contained naturally occurring ochres. Black pigments could be produced from carbon sources such as charcoal or soot. These materials are inherently stable, but material selection alone cannot explain the extraordinary preservation. The real mystery lies in the interaction between pigments, plaster, and environment. Researchers discovered that Roman painters frequently applied pigments onto carefully prepared plaster surfaces. During the fresco process, pigments bonded chemically with wet lime plaster as it cured. This created a durable integration between colour and wall rather than a simple painted layer sitting on the surface. However, many questions remain unanswered. How did Roman craftsmen consistently achieve such effective chemical bonding without modern chemistry? How did they determine optimal curing conditions? How did they select pigment mixtures capable of resisting centuries of underground environmental change? Some tombs display preservation levels that vary dramatically even within the same chamber. Certain sections remain vibrant, while adjacent areas deteriorated significantly. This suggests Roman artisans may have used different techniques, recipes, or material sources. Advanced spectroscopic studies continue investigating these questions, yet no complete explanation exists. The survival of these colours represents not merely artistic success, but technological success. Every preserved pigment particle is evidence of practical chemical knowledge, developed nearly 2,000 years before modern materials science emerged. Another remarkable feature involves environmental stability. The underground location accidentally created a protective microclimate. Temperatures remained relatively stable compared with surface conditions. Direct sunlight never reached painted walls. Wind erosion was absent. Yet, passive protection alone cannot fully explain preservation. Archaeologists identified drainage features and construction details, suggesting Roman builders intentionally managed moisture. Small architectural modifications appear designed to reduce water infiltration and improve air circulation. The exact effectiveness of these systems remains debated. Some researchers believe Roman engineers understood far more about environmental management than surviving written records indicate. Others argue that favourable geological conditions contributed significantly to preservation. The truth may involve both factors. The necropolis reveals remarkable standardization. Bricks, architectural proportions, burial layouts, and decorative patterns remain consistent across multiple structures, suggesting organized production and quality control. This raises a key question. How did an empire spanning over 5 million square kilometers maintain construction standards without modern communication? Similar building techniques appear from Britain to Syria, and the Via Triumphalis necropolis offers a revealing example of this vast technological network. Pohansko is an ancient fortified settlement located in the floodplains of the Dyje River near Břeclav in the present-day Czech Republic, covering nearly 28 hectares and protected by massive defensive earthworks. It was one of the largest centres of Great Moravia during the 9th century. Yet beneath its walls lies a technological mystery that archaeologists still struggle to fully explain. How did a society without modern machinery, advanced mathematics, or written engineering manuals construct, organise, and operate a complex fortified centre whose industrial capabilities rivaled many larger medieval cities? The modern discovery of Pohansko began in the 1950s, when systematic archaeological investigations were launched by researchers from Masaryk University. What initially appeared to be a medieval fortification soon revealed itself as one of the most important Great Moravian sites ever discovered. Decades of excavation uncovered churches, workshops, residences, cemeteries, roads, defensive structures, and evidence of large-scale industrial production. The findings transformed Pohansko from a regional archaeological site into a key location for understanding one of Europe's most enigmatic early medieval civilizations. The first mystery concerns the enormous defensive system surrounding the settlement. Archaeological surveys revealed ramparts extending approximately 2 kilometers around the central fortified area. These defenses consisted of complex layers of timber, earth, and stone. Unlike simple earthen embankments, The walls incorporated sophisticated wooden frameworks designed to reinforce the structure and prevent collapse. Some sections reached several meters in height and required thousands of cubic meters of material. The engineering challenge becomes apparent when comparing the construction effort with known labor capabilities. Building such fortifications would have required the harvesting, transportation, and placement of thousands of large trees. Modern experimental archaeology suggests that cutting a mature oak using period tools could require several hours of labor. When multiplied across the timber required for the entire defensive system, the project represents an enormous organizational achievement. Yet archaeologists have found little evidence describing how such a workforce was coordinated. The walls exist, but the administrative system that made them possible remains largely invisible. The second mystery involves the location itself. Pohansko was established in a landscape dominated by river channels, wetlands, and periodically flooded terrain. Modern engineers generally avoid constructing large settlements on unstable floodplain soils without extensive foundation preparation. Yet the inhabitants of Pohansko successfully built churches, workshops, roads, and defensive structures that remained functional for generations. Excavations revealed evidence of carefully layered foundations and deliberate ground stabilization. Builders appear to have selected specific soil compositions for different structural purposes. Some areas show signs of engineered drainage systems that redirected water away from important buildings. The remarkable aspect is that these solutions were developed centuries before the emergence of modern geotechnical science. Researchers understand what was built, but not fully how the builders acquired the knowledge necessary to manage such a difficult environment. The third, and perhaps most fascinating mystery centers on the metallurgical workshops of Pohansko. Among the most important discoveries at the site are industrial areas dedicated to iron production and metalworking. Archaeologists uncovered furnaces, slag deposits, tools, unfinished products, and evidence of specialized manufacturing zones. These remains reveal a level of technical sophistication that raises difficult questions about early medieval engineering knowledge. Iron production is far more complex than simply heating ore. The quality of a finished blade, tool, or weapon depends heavily on precise temperature control, airflow regulation, fuel management, and cooling techniques. Modern metallurgical analysis of artifacts from Great Moravian sites has revealed surprisingly consistent material properties. Many tools exhibit hardness levels and structural characteristics, indicating that smiths understood how to manipulate metal through controlled heating and forging processes. The mystery lies in how they achieve this precision. Temperatures inside bloomery furnaces often exceeded 200 degrees Celsius. Maintaining such conditions without thermometers requires extraordinary practical knowledge. A difference of only a few hundred degrees can dramatically affect the quality of the resulting iron. Yet many artifacts recovered from Pohansko display remarkably consistent craftsmanship. Experimental reconstructions have shown that bloomery furnaces are extremely sensitive systems. Small variations in charcoal quality, airflow, or ore composition can produce vastly different outcomes. Nevertheless, the metalworkers of Pohansko repeatedly produced functional weapons, agricultural tools, and specialized equipment. Some archaeologists believe generations of accumulated experience allowed smiths to recognize precise temperatures by observing flame color, spark behavior, and metal appearance. Others argue that the consistency suggests the existence of standardized production techniques passed through formal apprenticeship systems. Even more intriguing is evidence for specialized industrial organization. Excavations indicate that certain sections of Pohansko were dedicated specifically to metalworking activities. This suggests that production was not random or household-based, but concentrated within designated industrial zones. Such specialization resembles patterns observed in much larger urban centers. The question remains whether these workshops operated independently or under centralized political control. The fourth mystery concerns long-distance resource acquisition. Iron production consumes enormous quantities of raw materials. Producing a single kilogram of usable iron can require several kilograms of ore and substantial amounts of charcoal. Large-scale manufacturing therefore depends on reliable supply networks. Researchers have identified evidence suggesting that materials arrived from multiple regions. Timber, ore, food supplies, and construction materials had to be transported into the settlement on a continuous basis. Maintaining such logistics within a 9th century economy would have required coordination across vast territories. Yet few written records survive to explain how these networks functioned. The fifth mystery involves the surprising degree of urban planning. Excavations revealed organized zones containing religious buildings, elite residences, workshops, defensive structures, and residential areas. The arrangement appears deliberate rather than accidental. Roads connected major sectors, while important buildings occupied strategically advantageous locations. This level of planning challenges older assumptions about Great Moravian settlements. Rather than representing a loosely organized tribal center, Pohansko increasingly resembles an early urban complex. Similar planning principles can be observed in contemporary Carolingian centers of Western Europe, yet the exact methods used by Great Moravian builders remain poorly understood. The sixth mystery concerns woodworking technology. Because wood decomposes over time, much of the original architecture has disappeared. However, post holes, foundation traces, and preserved fragments reveal the existence of large timber structures. Some buildings would have required advanced joinery techniques capable of supporting significant loads. The problem for archaeologists is that most of the evidence has vanished. The surviving traces indicate impressive construction capabilities, but the specific engineering methods remain largely lost. Entire categories of technical knowledge may have disappeared with the craftsmen who developed them. The seventh mystery is perhaps the most perplexing of all: the sudden decline of the system. During the early 10th century, Great Moravia entered a period of political instability. Pohansko eventually lost its importance, and many of its industrial activities ceased. The workshops fell silent. The defensive walls deteriorated. The administrative networks disappeared. Civilizations often collapse, but what makes Pohansko remarkable is how much technical knowledge seems to have vanished alongside the settlement itself. The engineers who stabilized floodplain soils, the smiths who controlled furnace temperatures exceeding 1,200 degrees Celsius, the builders who organized massive construction projects, planners who designed one of the largest fortified centers in Central Europe, all disappeared from history without leaving detailed explanations of their methods. Located near modern Vetren in central Bulgaria, deep within territory once controlled by the Thracian kingdom, Pistyros emerged as one of the most unexpected commercial centers of the ancient world. Archaeological excavations began in 1988 after local discoveries revealed massive stone fortifications hidden beneath farmland. As researchers uncovered more of the settlement, a deeper mystery began to take shape. The question is not why Pistyros existed, but how a Greek trading community situated hundreds of kilometers from the Aegean coast managed to develop advanced infrastructure, extensive international trade connections, and sophisticated urban engineering capabilities that remain only partly understood today. First mystery begins with geography. Most Greek colonies were established along coastlines. Maritime transport was the backbone of the ancient Greek economy because sea transport was vastly more efficient than overland movement. Historical studies suggest that transporting goods by land could cost several times more than transporting the same cargo by sea. Pistyros broke this rule. The settlement was located deep within the interior of Thrace, approximately 200 kilometers from the nearest major Aegean ports. Yet, archaeological discoveries reveal that large quantities of imported goods reached the city. Pottery from Thasos, amphorae from the northern Aegean, luxury goods, metal products, and coins circulated through the settlement. This raises a difficult technological question. How was a large-scale commercial supply chain maintained across hundreds of kilometers of rivers, mountains, forests, and tribal territories without paved Roman roads, wheeled freight networks, or centralized imperial infrastructure? Modern logistics relies on highways, fuel, telecommunications, and satellite navigation. Pisteros operated more than 300 years ago without any of these advantages. Some researchers believe the city functioned as part of a highly organized trade corridor linking the Aegean world with the interior Balkans. The problem is that archaeologists still cannot fully reconstruct the transportation system that made such commerce possible. The economic network existed, but the physical mechanisms behind it remain only partially visible. One of the most impressive discoveries at Pisteros is its massive defensive wall system. The fortifications were constructed from granite blocks and stone foundations reaching considerable thickness. Excavations revealed carefully planned gates, towers, and defensive sections integrated into a coherent urban layout. At first glance, this may seem ordinary. However, the construction raises significant technical questions. Granite is one of the hardest stones commonly used in ancient architecture. Its compressive strength can exceed 130 megapascals, making it extremely durable but difficult to quarry and shape. Extracting, transporting, and positioning large granite blocks requires substantial engineering knowledge. The challenge becomes even greater when considering the location. Unlike coastal Greek cities with direct maritime access to stone quarries and shipping routes, Pisteros was located far inland. Every construction material had to be obtained locally or transported through difficult terrain. Archaeologists can measure the walls, analyze the stone, and reconstruct portions of the design. What remains unclear is how builders coordinated the extraction, transportation, and assembly of thousands of tons of material using only Iron Age technology. The engineering system that enabled construction remains largely invisible. Perhaps even more surprising than the walls is the city plan itself. Excavations reveal evidence of organized streets, residential zones, commercial districts, storage areas, and infrastructure arranged according to principles commonly associated with Greek urban planning. This is remarkable because Pisteros was not located in mainland Greece. It was situated within Thrace, a region traditionally portrayed as politically fragmented and less urbanized than the Greek city-state. Yet the settlement displays evidence of planning rather than organic growth. Urban planning requires surveying requires measurement, and measurement requires standardization. The mystery is not whether the city was planned, because the archaeological evidence strongly suggests that it was. The mystery is how surveyors established accurate layouts without modern instruments. Today, engineers use laser levels, GPS receivers, and digital mapping systems, while ancient builders relied on ropes, plumb bobs, sighting tools, and geometry. Despite these limitations, the city achieved a level of organization that continued functioning for generations. Exactly how that precision was maintained remains uncertain. No city can survive without water. This was especially true for Pisteros because commercial centers require reliable supplies, not only for drinking but also for food preparation, sanitation, craft production, and livestock. Excavations have revealed drainage systems, water control features, and infrastructure designed to manage seasonal rainfall. At first glance, these systems appear simple, yet hydraulic engineering is often deceptive. Even small drainage networks require careful calculations of gradient, flow velocity, runoff volume, and erosion resistance. Modern engineers use mathematical models to predict water movement, whereas ancient engineers relied entirely on experience. The remarkable fact is that many ancient drainage systems functioned successfully for centuries, and Pisteros appears to have been no exception. The unanswered question is how local builders acquired and transmitted this hydraulic knowledge generation after generation without technical manuals or formal engineering schools. One of the most extraordinary discoveries from Pisteros is the large number of coins recovered from the site. Hundreds of coins originating from different regions reveal a highly active commercial economy. The city clearly participated in long-distance trade networks spanning much of the Balkans and the northern Aegean. This evidence creates a major paradox. The financial activity is visible, but the financial system is not. Modern commerce leaves contracts, invoices, receipts, databases, and banking records. Ancient Pisteros left almost none. How were transactions verified? How were debts recorded? How were exchange rates established between different currencies? How were commercial disputes resolved? The famous veteran inscription demonstrates that merchants possessed legal protections and commercial privileges. However, it does not explain how the daily economic machinery actually operated. The economic engine existed, but most of its operating mechanisms have disappeared. Trade cities do not exist in isolation. They require workshops, storage facilities, repair centres, craftsmen, transport services, and administrative support. Archaeologists have discovered evidence of manufacturing activity, metalworking, storage structures, and commercial operations. Yet many of the industrial facilities that should have supported such extensive trade remain unidentified. This creates another mystery. Was much of the industrial activity constructed from wood and other perishable materials that vanished over time? Did production occur outside the excavated area, or has a significant portion of the settlement simply not been discovered yet? The site currently covers only a fraction of what may once have existed. Future excavations could dramatically alter our understanding of how the city functioned. The greatest mystery of Pisteros may not be physical technology at all. It may be organizational technology. The city functioned as part of a complex system involving Greek merchants, Thracian rulers, regional producers, transport operators, craftsmen, and foreign trading partners. Coordinating such a network required communication, legal frameworks, taxation systems, security arrangements, and logistical planning. Modern corporations use computers, accounting software, telecommunications networks, and real-time data analysis to manage comparable operations. Pisteros managed its network without any of these tools, yet the settlement survived and prospered for centuries. This suggests that ancient administrators possessed sophisticated methods of organization that archaeology can rarely detect. The buildings survive, but the paperwork does not. The infrastructure survives, but the management system has almost completely vanished. Ratiaria is an ancient Roman city on the southern bank of the Danube River in northwestern Bulgaria. Once one of the most important military and industrial centres on Rome's northern frontier, it presents a technological mystery that archaeologists still cannot fully explain. How did a frontier city located more than 500 kilometres from Rome develop industrial capabilities, logistical networks, and engineering infrastructure comparable to some of the empire's greatest urban centres? The ruins of Ratiaria were identified near the modern village of Archar, Bulgaria. Systematic archaeological investigations began during the 20th century, revealing remains of streets, fortifications, workshops, public buildings, and industrial facilities. Excavations confirmed that the city became Colonia Ulpia Ratiaria under Emperor Trajan around the early 2nd century AD after Rome's conquest of Dacia. Yet many of its greatest secrets remained buried or were destroyed by decades of illegal excavations before modern archaeology could fully document them. The first mystery concerns the scale of Ratiaria itself. Most Roman frontier settlements were designed primarily as military outposts. They served defensive functions, housed troops, and controlled trade routes. Ratiaria evolved into something far larger. Archaeological surveys indicate that the urban area may have covered more than 30 hectares during its peak. Monumental public buildings, administrative complexes, warehouses, workshops, and residential districts occupied the landscape along the Danube frontier. The question is why? The city stood on the edge of territories frequently threatened by invasions. Large-scale urban investment in such regions carried enormous risks. Yet Roman authorities transformed Ratiaria into one of the most important cities of the Balkan provinces. The logistical challenge alone was extraordinary. Millions of kilograms of stone, timber, metal, ceramics, and construction materials had to be transported across vast distances. Even with Roman roads, moving building materials hundreds of kilometers required sophisticated planning. Modern researchers often compare Roman logistics to pre-industrial supply chains. Historians estimate that maintaining a single Roman legion of approximately 5,000 soldiers required hundreds of tons of food and equipment every year. Ratiaria supported military forces, civilian populations, industries, and river fleets simultaneously. How Roman administrators coordinated such operations with no modern communications systems remains only partially understood. The second mystery is perhaps the most remarkable. Excavations have uncovered evidence that Ratiaria was not merely a military city. It was also an industrial centre capable of large-scale metal production. Archaeologists discovered slag deposits, furnace remains, casting debris, unfinished metal objects, and evidence of specialised workshops. These findings indicate extensive metallurgical activity over centuries. The scale of production is what puzzles researchers. Roman metallurgy was already advanced by ancient standards. Across the empire, iron production supported armies, agriculture, mining, transportation, and construction. However, evidence from Ratiaria suggests a concentration of industrial activity far greater than expected for a frontier settlement. Some researchers believe the city may have supplied weapons, armour, tools, nails, fittings, and military hardware for multiple sectors of the Danube frontier. To understand the challenge, consider the energy requirements. Producing 1 kilogram of iron in ancient bloomery furnaces could require several kilograms of charcoal. Large-scale iron production therefore consumed enormous quantities of wood. Experimental archaeology demonstrates that ancient furnaces often operated at temperatures exceeding 1,100 to 1,200 degrees Celsius. Maintaining such temperatures required precise airflow management and carefully controlled fuel supplies. The mystery is where all the fuel came from. Archaeological evidence has not yet fully identified the forest management systems necessary to sustain centuries of industrial production. If Ratiaria operated hundreds of furnaces over long periods, surrounding forests should show evidence of intensive exploitation. Yet the scale of deforestation predicted by modern models does not perfectly match available archaeological evidence. This discrepancy has produced competing theories. One hypothesis suggests that timber was transported along the Danube from distant regions. Another proposes systematic forest management practices that remain poorly documented. A third suggests that industrial activity may have fluctuated significantly rather than operating continuously. None of these explanations completely solve the problem. The sophistication of the furnaces themselves raises additional questions. Roman metallurgists lacked modern thermometers, yet they consistently achieved temperatures sufficient for complex metalworking. Chemical analysis of Roman iron artifacts often reveals surprisingly uniform carbon distribution and quality control. In some cases, Roman weapons exhibit metallurgical characteristics comparable to much later pre-industrial technologies. How craftsmen monitored furnace conditions without scientific instruments remains a subject of ongoing research. The production chain was equally complex. Ore had to be mined, transported, sorted, crushed, smelted, refined, forged, inspected, and distributed. Every stage required skilled specialists. Some historians compare the organizational complexity of Roman metallurgy to an early industrial system operating nearly 1,800 years before the Industrial Revolution. A third mystery involves water. Excavations have uncovered evidence of drainage systems, underground channels, water pipes, reservoirs, and public infrastructure. Maintaining reliable water supplies was especially difficult in frontier environments, subject to seasonal flooding from the Danube. Roman engineers understood hydraulic principles with remarkable sophistication. Aqueduct gradients were often maintained within fractions of a percent over many kilometers. Water systems had to balance flow rates, pressure, sediment accumulation, and structural stability. Yet only fragments of Ratiaria's hydraulic network survive. The full design remains unknown. Researchers suspect the city possessed a far more extensive water management system than currently documented. Portions may remain buried beneath agricultural land, while others were destroyed long ago. Without complete excavation, engineers can only reconstruct parts of the original network. Ratiaria served as a major Danube port. This role created another mystery. The Danube stretches approximately 2,850 kilometers, making it one of Europe's most important rivers. Roman control of the river required fleets of patrol vessels, transport ships, supply barges, and military craft. Historical evidence suggests Ratiaria played an important role in supporting these operations, yet surprisingly little direct evidence of shipbuilding facilities survives. Where were the dry docks? Where were the repair yards? Where were the warehouses that stored timber, sails, ropes, anchors, and naval equipment? The scale of river operations implied by historical records exceeds the infrastructure currently identified through archaeology. Some facilities may lie beneath unexcavated areas. Others may have been destroyed beyond recognition. The absence of evidence remains one of the city's greatest puzzles. Fragments of mortar and concrete recovered from Ratiaria have attracted scientific interest. Many Roman structures survived nearly 2 millennia despite earthquakes, flooding, temperature fluctuations, and warfare. Recent studies on Roman concrete elsewhere in the empire have revealed self-healing mechanisms involving limeclasts and complex chemical reactions. These properties allow cracks to reseal over time when exposed to water. Whether similar techniques were employed at Ratiaria remains uncertain. Material analyses indicate local adaptations to regional environmental conditions. Builders may have modified mortar compositions using locally available aggregates and minerals. The exact formulas, however, remain largely unknown. Many samples disappeared before detailed laboratory analysis became possible. Perhaps the greatest mystery is not ancient at all. During the late 20th and early 21st centuries, Ratiaria suffered extensive looting. Thousands of illegal excavation pits appeared across the site. Heavy machinery damaged archaeological layers. Countless artifacts were removed without documentation. For archaeologists, context is often more valuable than the artifact itself. A coin found in its original layer can reveal chronology, trade, economics, and human activity. The same coin removed without context loses much of its scientific value. At Ratiaria, entire sections of history disappeared before researchers could investigate them. This destruction created permanent gaps in the archaeological record. Future discoveries may answer some questions, but others may never be solved. Augusta Traiana lies beneath the modern city of Stara Zagora in central Bulgaria and remains one of the most remarkable Roman archaeological sites in the Balkans. Archaeologists first identified significant remains during 19th century construction projects, while systematic excavations throughout the 20th century revealed forums, streets, public buildings, water systems, and defensive structures. Yet beneath these ruins lies a technological mystery that continues to challenge researchers. How did Roman engineers create and maintain such a highly organized urban center in a region exposed to earthquakes, invasions, and centuries of environmental change, while leaving behind engineering solutions that are still not fully understood today? The visible ruins of Augusta Traiana represent only a fraction of the original city. Founded during the reign of Emperor Trajan in the early 2nd century AD, the settlement grew into one of the most important Roman centers in the Balkans. Archaeological surveys suggest that large portions of the ancient city remain hidden beneath modern development. What researchers have already uncovered reveals a level of planning and technical sophistication that raises important questions about Roman engineering capabilities. One of the most striking discoveries at Augusta Traiana is the remarkable precision of its street network. Excavations have revealed major roads intersecting at nearly perfect right angles, forming a carefully organized urban grid. Such layouts were common in Roman cities, yet the execution at Augusta Traiana remains impressive because the builders achieved this precision across a large urban area without modern surveying instruments. Today, engineers rely on laser rangefinders, satellite positioning systems, and digital mapping software. Roman surveyors possessed none of these technologies. Instead, they worked with simple instruments such as the groma, measuring rods, plumb lines, and astronomical observations. Despite these limitations, the alignment of streets, public squares, and major buildings demonstrates an extraordinary level of accuracy. The challenge becomes even more significant when considering scale. Maintaining angular consistency across several hectares requires cumulative measurement and errors to remain extremely small. Modern civil engineers recognize how quickly tiny inaccuracies can multiply during large construction projects. Yet Augusta Traiana displays a degree of geometric control that suggests Roman surveyors possessed highly refined field methods whose practical details remain only partially understood. Every large Roman city depended on water. Public baths, fountains, workshops, households, and sanitation systems required enormous quantities of clean water every day. Augusta Traiana was no exception. However, one of the greatest mysteries concerns how engineers managed water distribution with such efficiency. Archaeological excavations have uncovered portions of pipelines, drainage channels, reservoirs, and underground conduits. These systems relied entirely on gravity. No electric pumps existed. No computerized monitoring systems regulated flow. Every gradient had to be calculated manually. Even a small mistake could cause water stagnation, flooding, or system failure. Yet many Roman hydraulic systems functioned successfully for centuries. Some surviving channels at Augusta Traiana display gradients so carefully controlled that modern engineers still study Roman hydraulic design principles for comparison. The mystery deepens because researchers have not yet identified every component of the original network. Geophysical surveys indicate that substantial underground structures remain undiscovered beneath the modern city. Some archaeologists suspect that additional reservoirs, distribution tanks, or pressure regulation systems may still lie hidden. Until those structures are found, the complete hydraulic design remains unknown. If supplying water was difficult, removing it may have been even harder. Beneath Augusta Traiana lies an extensive drainage system constructed from stone, brick, and mortar. The network carried wastewater away from streets, homes, workshops, and public facilities. In some areas, archaeologists discovered channels large enough for maintenance access. The engineering challenge involved maintaining consistent flow over long distances. Modern drainage systems depend on sophisticated calculations, computer modeling, and precision equipment. Roman engineers achieved comparable functionality using simple tools and empirical knowledge. Many drainage channels remain structurally intact despite nearly 2,000 years of earthquakes, seasonal flooding, soil movement, and urban development. Some sections continue to demonstrate remarkable resistance to collapse. Researchers still debate how Roman builders determined optimal slopes across such large areas. The answer likely involved a combination of surveying techniques, accumulated engineering knowledge, and practical experimentation. Yet the exact procedures remain largely speculative because surviving technical documentation is incomplete. The Balkan region has experienced numerous seismic events throughout history. Historical records indicate that major earthquakes affected many cities across the region during Roman and post-Roman periods. This raises an important question. Why did portions of Augusta Traiana survive? Excavated foundations reveal complex construction methods involving layered materials, stone reinforcements, and concrete cores. In some structures, appear to have combined different materials strategically to distribute loads and absorb stress. Modern earthquake-resistant construction often relies on flexibility rather than absolute rigidity. Interestingly, some Roman structures display characteristics consistent with this principle. Certain walls exhibit evidence of controlled deformation rather than catastrophic failure. The mystery is not whether Roman engineers understood seismic mechanics in a scientific sense. They almost certainly did not possess modern geological theory. The mystery is whether centuries of practical observation allowed them to develop construction techniques that inadvertently improved earthquake resistance. Comparisons with other Roman sites such as Pompeii, Ephesus, and cities throughout Anatolia suggest that regional builders may have adapted their methods according to local conditions. Augusta Traiana could represent one example of this lost practical engineering knowledge. Perhaps no aspect of Roman engineering generates more scientific interest today than construction materials. Concrete, mortar, brick, and stone from Augusta Traiana continue to survive after nearly 19 centuries. Modern reinforced concrete structures often require major repairs within decades, yet many Roman structures remain recognizable after 2 millennia. Laboratory analyses of Roman mortars have revealed highly complex mineral compositions. Chemical reactions between lime, volcanic materials, and aggregates sometimes produced self-strengthening properties over time. Researchers studying ancient Roman concrete have identified mineral formations capable of increasing durability rather than reducing it. Although Augusta Traiana did not use the same materials as coastal Roman harbours, its construction demonstrates comparable longevity. Scientists continue investigating whether regional variations in Roman mortar recipes contributed to exceptional durability. The unanswered question is how much Roman builders truly understood about the chemical processes involved. Were these mixtures the result of scientific knowledge, practical experimentation, or generations of accumulated craftsmanship? No definitive answer exists. Unlike archaeological sites abandoned centuries ago, Augusta Traiana remains buried beneath a living city. This creates one of the greatest challenges in Roman archaeology. Excavations can only occur in limited areas. Vast portions of the ancient city remain inaccessible beneath roads, buildings, and modern infrastructure. Ground-penetrating radar, magnetometry, and geophysical imaging have revealed anomalies indicating buried structures across large sections of Stara Zagora. These may include additional public buildings, workshops, warehouses, residential districts, and sections of infrastructure. The scale of the hidden remains suggests that current knowledge represents only a fraction of the original city. Future discoveries could dramatically change existing interpretations of Roman urban engineering in the Balkans. In some respects, Augusta Traiana resembles a giant archaeological puzzle in which most pieces remain concealed underground. Researchers can observe fragments of the design, but not the complete picture. Dresnik is a Roman archaeological site in western Kosovo that preserves one of the most puzzling technological mysteries of the late ancient world. How did a remote provincial settlement acquire the resources, engineering knowledge, and artistic capabilities normally reserved for the great imperial centres of the Roman Empire? The site lies near the modern village of Dresnik, approximately 20 kilometers west of Peja in Kosovo. At first glance, it appears to be just another Roman ruin scattered across the Balkans. Yet beneath the soil lies evidence of architecture, defensive engineering, and artistic craftsmanship so sophisticated that archaeologists continue to debate the true status of the settlement. The greatest mystery is not that Romans built impressive structures here. The real mystery is why such extraordinary technology appeared in a location that should never have possessed it. The modern discovery of Dresnik occurred during archaeological investigations in the early 21st century. Excavations revealed the remains of a monumental Roman complex dating primarily to the 4th century AD, During the turbulent decades when the Roman Empire struggled to maintain control across its vast territories, what researchers expected to find was a provincial villa. What emerged instead was something far more complicated, a fortified complex featuring massive walls, ceremonial halls, advanced heating systems, imported luxury materials, and some of the finest mosaic floors ever discovered in Kosovo. The first and perhaps greatest mystery concerns the mosaics themselves. Archaeologists uncovered extensive mosaic floors covering large sections of the complex. This alone was remarkable. Throughout the Roman world, mosaic decoration was expensive. Wealthy homeowners often reserved mosaics for reception halls, dining rooms, or baths. Even luxurious villas rarely decorated every important space with elaborate mosaic artwork. Yet at Dresnik, large portions of the complex appear to have been adorned with intricate geometric designs created from thousands upon thousands of carefully cut tesserae. The scale creates an immediate problem. To manufacture mosaic floors of this quality required specialized craftsmen. Every tessera had to be quarried, cut, transported, sorted by color, and placed according to a carefully planned design. Studies of Roman mosaics elsewhere suggest that experienced workshops could lay only a limited area per day while maintaining geometric accuracy. Some estimates indicate that a skilled mosaic team might complete only a few square meters of highly detailed work daily. This means the floors at Dresnik likely required months or even years of coordinated labor. The mystery deepens when the geometry is examined. Many Roman mosaics contain repeating patterns. Repetition may look simple, but maintaining perfect symmetry across large surfaces is an engineering challenge. Modern builders rely on laser levels, measuring tapes, and digital planning software. Roman craftsmen possessed none of these tools, yet the geometric patterns discovered at Dresnik remain remarkably consistent across large floor surfaces. Small measurement errors should have accumulated over distance, causing visible distortions. Instead, the designs retain their proportional relationships with surprising precision. How was this achieved? Some researchers suggest the use of grids, cords, wooden measuring rods, and chalk guidelines. Yet no surviving documentation explains the exact methods employed by mosaic workshops operating in provincial regions of the empire. The technical knowledge required to coordinate hundreds of thousands of tesserae remains only partially understood. The mosaics of Dresnik rival decorative programs found in elite sites such as Mediana in Serbia or Felix Romuliana, both associated with imperial power. Why a settlement in western Kosovo possessed comparable artistic capabilities remains one of the site's great puzzles. The second mystery involves the monumental hall discovered within the complex. Archaeologists identified an aula, or ceremonial hall, measuring approximately 22 meters long and 11 meters wide. Such dimensions are not typical for ordinary rural estates. Large audience halls were symbols of authority. They were spaces where governors received visitors, officials conducted administration, and powerful individuals displayed status. The question is simple: who required such a building? The surrounding region was not Rome. It was not Constantinople. It was not Thessalonica. These cities served as major political and economic centers. Dresnik occupied a comparatively remote position within the empire, yet the architecture suggests access to resources on a scale far beyond what historians would normally expect from a local landowner. This has led some scholars to propose that the complex may have served a governmental or imperial function. Others argue that it belonged to an exceptionally wealthy aristocrat. Neither explanation fully resolves the problem. The architecture appears too ambitious for a normal villa, yet too isolated for a major administrative capital. The third mystery concerns the enormous defensive walls. Excavations revealed fortifications approximately 3.7 meters thick in some areas. Circular towers may have reached diameters between 10 and 16 meters. These are not symbolic structures. They represent serious military engineering. Defensive walls require enormous investments in labor and materials. Thousands of tons of stone had to be extracted, transported, shaped, and assembled. Every metre of wall represented a commitment of manpower, food supplies, engineering knowledge, and logistical coordination. But what exactly were these defences protecting? If the complex was merely an agricultural estate, the fortifications seem excessive. If it functioned as a military centre, evidence for large garrisons remains limited. If it served an imperial role, historians still struggle to explain why such an important facility was established here. The contradiction remains unresolved. The fourth mystery involves Roman heating technology. Evidence indicates the presence of a hypercourse system, one of the most advanced heating technologies of the ancient world. A hypercourse functioned by circulating hot air beneath raised floors and within wall cavities. The system transformed buildings into giant thermal machines capable of maintaining comfortable indoor temperatures even during harsh winters. Constructing a hypercourse required precision engineering. Brick pillars had to support elevated floors. Furnace chambers needed carefully controlled airflow. Heat distribution required sophisticated understanding of architecture and thermodynamics, even if Roman engineers did not possess modern scientific terminology. The challenge becomes even greater when fuel consumption is considered. Large hypercourse systems demanded continuous supplies of wood. A single heated complex could consume enormous quantities of fuel over the course of winter season. Maintaining such a system required organized forestry, transportation networks, storage facilities, and skilled operators. Yet many details remain unknown. Researchers can reconstruct the physical structures, but they cannot fully explain how daily operations were managed. Questions about fuel procurement, maintenance schedules, labour organisation, and thermal efficiency remain subjects of ongoing debate. The fifth mystery concerns long-distance logistics. Luxury materials discovered at the site suggest access to trade networks extending across the Balkans and beyond. Marble, decorative stone, glass, metal objects, and specialized construction materials had to travel considerable distances before reaching Dresnik. Modern transportation systems make such movements seem ordinary. In the 4th century, it was anything but ordinary. Moving heavy cargo over land required wagons, draft animals, roads, bridges, labourers, and administrative coordination. Roman logistics were impressive, but the presence of high-status materials in a relatively remote location raises difficult questions about the site's economic importance. Why would merchants and officials devote so many resources to supplying this settlement? No surviving written record provides a definitive answer. The 6th mystery may be the most exciting of all. Many archaeologists suspect that only a fraction of the ancient settlement has been excavated. Geophysical surveys suggest additional structures remain buried beneath surrounding fields. Scattered finds indicate a larger urban landscape than originally imagined. This possibility changes everything. If the visible remains represent only the central core of a much larger settlement, then current interpretations may be fundamentally incomplete. The monumental hall, luxury mosaics, and defensive walls could be components of a forgotten Roman centre, whose true extent remains hidden underground. Entire districts may still await discovery. Workshops, administrative buildings, residential quarters, storage facilities, and religious structures could lie beneath the landscape, invisible to the naked eye. Almetum is a Roman fortress city in Dobruja, Romania. Surrounded today by quiet fields near the lower Danube frontier, it preserves one of the most overlooked engineering mysteries of the late Roman world. How did ancient military engineers construct a defensive system so durable, so geometrically precise, and so strategically advanced that portions of its design still appear surprisingly modern more than 1,600 years later? The site lies near the modern village of Pantelimonul de Sus in southeastern Romania. To most visitors, Almetum appears to be little more than the remains of stone walls and collapsed towers. Yet, beneath those ruins lies evidence of engineering knowledge that continues to puzzle archaeologists. The mystery is not merely how the fortress was built. The greater mystery is how Roman engineers operating on a dangerous frontier repeatedly rebuilt, reinforced, and optimized the city despite invasions, economic crises, and the eventual collapse of imperial authority. The modern discovery of Ulmitum began in the early 20th century. Systematic excavations led by the Romanian archaeologist Vasil Pavan revealed the remains of a fortified Roman settlement occupying a strategic position within the defensive network of Scythia Minor. Further investigations uncovered walls, gates, towers, inscriptions, workshops, streets, and evidence of multiple construction phases spanning several centuries. What initially appeared to be another Roman frontier fort soon revealed something more complex, a military settlement whose engineering solutions were far more sophisticated than expected for such a remote border region. The first mystery concerns the fortress walls themselves. Archaeological surveys show that the main defensive circuit enclosed an area of roughly 3 hectares. The walls reached approximately 3 meters in thickness in some sectors and were reinforced by numerous projecting towers. Constructing such a fortification required moving thousands of tons of stone. Unlike modern builders, Roman engineers had no hydraulic cranes, diesel machinery, laser surveying equipment, or computer-assisted design. Yet the walls display remarkable alignment and structural consistency. What makes this particularly mysterious is the fortress's history of destruction and reconstruction. Historical records indicate that the region experienced repeated invasions by Goths, Huns, Slavs, Avars, and other groups between the 3rd and 7th centuries AD. Many frontier settlements disappeared entirely under such pressure. Ulmitum, however, was repeatedly rebuilt. Archaeologists can identify multiple construction phases, showing that engineers continually strengthened weak points, modified defensive lines, and adapted the fortress to evolving military threats. The ability to maintain such large-scale engineering projects on a volatile frontier remains difficult to explain. Even today, sustaining major infrastructure in a conflict zone presents enormous logistical challenges. The second mystery involves Roman construction materials. Analysis of mortar samples from late Roman fortifications across the Danube frontier has demonstrated remarkable durability. Although Ulmitum's mortar composition varies between building phases, many sections continue to hold masonry together after more than 16 centuries of exposure. By comparison, many modern reinforced concrete structures require extensive repairs after only 50 to 100 years. Researchers studying Roman mortars have identified complex mineral reactions involving lime, volcanic components in some regions, and long-term crystallization processes that can increase durability over time. While Ulmitum does not possess the famous volcanic materials used in some Italian Roman concrete, its builders still achieved extraordinary structural longevity. The precise methods used to optimize local materials remain only partially understood. Archaeologists can identify ingredients, but reconstructing the practical knowledge possessed by Roman builders is far more difficult. The written instructions that once guided construction crews have largely vanished. The third mystery centers on logistics. Every stone used in Ulmitum had to be quarried, transported, shaped, and positioned. Estimates from Roman military engineering studies suggest that constructing even a medium-sized fortress required the movement of several thousand tons of building material. Transporting 1 ton of stone by animal power over rough terrain could consume significant manpower and resources. Yet Ulmitum was only one component of a vast frontier defense system stretching across hundreds of kilometers. This raises an important question. How did Roman administrators coordinate labor, supplies, transportation, and construction across such a massive region without modern communication systems? Messages traveled only as fast as horses could ride. Weather frequently disrupted movement. Frontier attacks could destroy supply routes. Nevertheless, Roman engineers repeatedly completed projects that would challenge many pre-industrial societies. The organizational mechanisms behind these achievements remain only partially understood because the administrative records have largely disappeared. The fourth mystery involves strategic planning. Almetum was not built in isolation. It formed part of a broader defensive network protecting the lower Danube frontier. Modern geographic analysis shows that many Roman forts occupied positions maximizing visibility, communication, and control of movement corridors. Some sites could potentially transmit warning signals across considerable distances through crew beacon systems or visual observation. What astonishes researchers is how effectively Roman planners selected these locations without access to satellite imagery, aerial surveys, or advanced topographic mapping. Modern military planners often rely on digital terrain models and sophisticated software to optimize defensive positions. Roman engineers achieved surprisingly effective results using only direct observation, experience, and surveying instruments. The methodologies behind this success remain difficult to reconstruct in detail because few technical manuals survive. The fifth and perhaps most fascinating mystery concerns Almetum's unusual polygonal defensive towers. Most people imagine Roman towers as simple squares or circles projecting from a fortress wall. At Almetum, however, several towers exhibit more complex geometric designs. These structures projected outward from the defensive circuit, creating wider fields of observation and reducing blind zones along the walls. The arrangement allowed defenders to attack enemies approaching from multiple angles while protecting adjacent sections of fortification. At first glance, this may seem obvious. Yet military architecture specialists note that these principles resemble concepts that became famous during the Renaissance, particularly in the development of star forts and angular bastions designed to maximize defensive fire coverage. The difference is that Almetum predates many of those innovations by more than 1,000 years. The geometry itself raises intriguing questions. Polygonal towers are more difficult to design and construct than simple rectangular structures. Every additional angle increases surveying complexity, stone cutting requirements, and structural challenges. Builders must carefully calculate wall intersections, load distribution, and defensive sightlines. Errors can create weaknesses rather than advantages. Why would Roman engineers choose such complicated designs on a frontier settlement? One explanation is accumulated battlefield experience. Roman military architects may have discovered through centuries of warfare that angular projections reduced vulnerable sectors along defensive walls. Another possibility is that engineers applied mathematical principles derived from Roman surveying traditions. The Romans possessed advanced knowledge of geometry, land measurement, and practical engineering. However, the exact calculations used by military designers remain largely unknown because few detailed architectural manuals survive. Even more intriguing is the possibility that these towers represented local experimentation. Frontier commanders constantly adapted defenses to specific threats. The polygonal towers of Almetum may reflect regional innovations developed by engineers responding to changing siege tactics. If so, they provide evidence that Roman military technology was far more flexible and adaptive than often assumed. Modern computer simulations of fortress defenses frequently demonstrate that even small changes in tower geometry can significantly alter defensive effectiveness. A difference of only a few degrees can affect visibility, missile coverage, and defensive reaction times. Yet Roman engineers achieved these optimizations without digital modeling. How they balanced practical experience and geometric planning remains one of the site's most compelling unanswered questions. The sixth mystery concerns water management. Sustaining a fortified settlement required reliable access to water during both peace and siege conditions. Excavations have revealed evidence of storage systems and infrastructure associated with water collection. However, archaeologists believe portions of the hydraulic network remain undiscovered. This uncertainty is significant because a fortress's survival often depended more on water than walls. Without adequate supplies, even the strongest defenses could fail within weeks. Roman engineers were masters of hydraulic technology, constructing aqueducts, reservoirs, drainage systems, and cisterns throughout the empire. Yet many details of Ulmetum's water infrastructure remain hidden beneath the ground or were destroyed during later occupation phases. Satserblia Cave is a prehistoric cave in western Georgia, near the foothills of the Caucasus Mountains. Archaeologists excavating the site uncovered evidence of human occupation dating between approximately 25,000 and 13,000 years ago. Among the discoveries were stone tools, animal remains, traces of ancient fireplaces, and one of the most important genetic finds ever recovered from the Ice Age. Yet the greatest mystery of Satserblia is not who lived there. The mystery is how a small community of hunter-gatherers developed survival technologies sophisticated enough to endure some of the harshest climatic conditions humans have ever faced. When humans occupied Satserblia, the world was very different. Large portions of northern Europe were covered by ice sheets, reaching several kilometers in thickness, and global temperatures during the last glacial maximum were approximately 4 to 7 degrees Celsius lower than today. In many regions, environmental conditions were hostile to long-term human settlement, yet the inhabitants of Satserblia survived. This raises a fundamental technological question. How did a relatively small group of hunter-gatherers maintain stable populations in such conditions without agriculture, domesticated animals, metal tools, or permanent infrastructure? Excavations revealed evidence of repeated occupation over thousands of years, suggesting that survival was not accidental. The inhabitants possessed reliable systems for acquiring food, producing clothing, managing fire, and adapting to seasonal environmental changes. Modern survival experts often emphasize that maintaining body temperature is one of the greatest challenges in cold environments, as hypothermia can become life-threatening within hours. Ice Age populations faced these risks continuously. Their survival implies technical knowledge that was transmitted across generations, yet almost none of that knowledge survives in written form. The cave preserves the results of this expertise, but not the methods themselves. One of the greatest puzzles surrounding Satserblia concerns clothing. No true textile fragments have survived and no leather garments remain, yet scientists know that the inhabitants could not have survived without sophisticated insulation systems. Archaeologists recovered stone scrapers and cutting tools displaying microscopic wear patterns associated with hide processing. Similar tools have been found at Upper Paleolithic sites across Eurasia and are often linked to the production of clothing. The problem is that clothing technology leaves very little archaeological evidence. Modern winter clothing relies on multiple insulating layers, moisture control and protection from wind. Ice Age communities lacked synthetic materials, yet they survived conditions that would challenge modern hikers equipped with advanced gear. Some researchers believe Upper Paleolithic populations developed tailored garments using bone needles and carefully processed animal hides, while others suggest the use of fur combinations optimized for thermal performance. The exact techniques remain unknown. What survives is indirect evidence, indicating that Ice Age clothing technology may have been far more sophisticated than traditional depictions of prehistoric people wrapped in simple animal skins. Fire appears throughout the archaeological layers of Satserblia. At first glance, fireplaces may seem ordinary, but in reality maintaining fire inside a cave environment is a highly complex problem. Too much smoke creates dangerous air quality, poor placement reduces heating efficiency, excessive heat damages living areas, and insufficient heat threatens survival. Modern engineers analyze airflow using computational fluid dynamics and advanced environmental modeling, but Ice Age communities had none of these tools. Yet the repeated placement of hearths within specific zones of the cave suggests deliberate planning. The inhabitants appear to have understood how air moved through the cave and may have selected locations that maximized warmth while minimizing smoke accumulation. How they acquired this knowledge remains uncertain. The mystery becomes even greater when considering that successful fire management would have required continuous monitoring over many generations, as small mistakes could have produced deadly consequences. The archaeological evidence reveals a successful system, but does not explain how the system was developed. The stone tools discovered at Satsublia reveal another surprising pattern. Many blades and cutting implements display remarkable consistency in size, shape, and manufacturing technique. Such standardization suggests more than simple trial and error. Modern manufacturing relies on quality control procedures to ensure that products meet specific requirements. While Ice Age societies obviously lacked factories, the repeated production of similar tools implies that technical knowledge was being taught according to established principles. Researchers have noted that Upper Paleolithic stone industries often required precise control over striking, angles, force application, and raw material selection. A mistake of only a few degrees could ruin an entire blade. This raises a fascinating question. How did communities without writing preserve such specialized knowledge across centuries or even millennia? The answer remains unknown. The consistency visible in the archaeological record suggests that prehistoric education systems may have been far more organized than traditionally assumed. One of the most difficult challenges facing any Ice Age community was food security. Animal remains recovered from Satsublia include species such as wild boar, red deer, and aurochs. These animals provided meat, fat, hides, and bone materials. But hunting alone does not explain long-term survival. Food availability changes throughout the year, and seasonal shortages can devastate small populations. Modern societies solve this problem through agriculture, refrigeration, transportation networks, and industrial food storage. The inhabitants of Satsublia possessed none of these systems, yet they endured. Some archaeologists suspect that advanced preservation methods may have been used, including drying, smoking, freezing, and underground storage. Others propose regional exchange networks connecting different groups across the Caucasus. Direct evidence remains limited. As a result, one of the most important technological systems supporting Ice Age survival remains largely invisible. In 2013, scientists extracted ancient DNA from a human temporal bone discovered inside Satsublia. The results transformed understanding of prehistoric Eurasia. Genetic analysis revealed a population now known as Caucasus hunter-gatherers, often abbreviated as CHG. This genetic lineage later contributed ancestry to populations across large portions of Europe and Western Asia. The discovery demonstrated that groups living in the Caucasus played a much larger role in human history than previously believed. Yet the finding created new mysteries. How did genetic influences originating in relatively small populations spread across thousands of kilometers? What migration routes connected distant regions? How extensive were social contacts during the late Ice Age? Ancient DNA provides answers to some questions while creating many more. Scientists can identify genetic relationships, but reconstructing the communication networks that enabled those relationships remains extremely difficult. Technology may have spread even more effectively than genes in prehistoric Europe. Similar stone tools, hunting methods, and survival skills appear across vast distances, suggesting that knowledge moved between groups long before writing existed. Despite relying only on memory and direct teaching, Ice Age communities preserved technical traditions for thousands of years. Satsublia may have been part of a wider information network linking human groups across Eurasia, though most evidence of it has disappeared. Srebrenik Fortress is a medieval stronghold in northeastern Bosnia and Herzegovina, perched on a limestone outcrop about 500 meters above sea level. First mentioned in historical records in 1333, it remains one of the best preserved fortresses in the Balkans. Yet beyond its military history lies a technological mystery that continues to challenge archaeologists, engineers, and historians alike. How did medieval builders construct, supply, and maintain a heavily fortified stone citadel on a nearly isolated rock summit, using only the tools and knowledge available more than 6 centuries ago? The fortress attracted modern archaeological interest through historical surveys conducted during the 19th and 20th centuries. Restoration efforts revealed multiple construction phases hidden beneath later modifications. Excavations uncovered defensive walls, towers, gateways, cisterns, and structural foundations built directly into the natural bedrock. These discoveries led researchers to an important conclusion. The fortress was not simply built on a mountain, it was carefully engineered into the mountain itself. The greatest mystery begins with the location. Srebrenik stands atop a steep rocky pinnacle separated from the surrounding terrain by deep natural slopes. Even modern visitors often wonder how builders transported construction materials to the summit. The walls contain thousands of tons of limestone blocks, mortar, timber supports, roofing materials, and defensive structures. Modern engineering projects facing similar terrain would typically rely on cranes, heavy lifting machinery, reinforced access roads, and detailed geological surveys. Medieval builders possessed none of these advantages, yet the fortress walls reach several meters in height and thickness, while conforming precisely to the irregular contours of the rock beneath them. Archaeologists estimate that constructing even a modest medieval fortress could require thousands of cubic meters of stone. A single cubic meter of limestone weighs approximately 2,400 kilograms. Transporting such quantities up a steep mountain without mechanized equipment would have required an extraordinary logistical operation. Historical records provide little information regarding the techniques used. Whether builders employed temporary wooden ramps, pulley systems, scaffolding networks, or methods now lost to history remains unknown. The mystery becomes even more fascinating when compared with other European fortresses. Many castles were built on elevated terrain, but relatively few occupy rock formations as isolated and difficult to access as Srebrenik. The challenge was not merely building walls. The challenge was delivering an entire construction industry to the summit. One of the most overlooked technological achievements at Srebrenik lies beneath the visible walls. The fortress has survived centuries of weather, warfare, earthquakes, and abandonment. Such durability suggests that its foundations were carefully integrated into the geology of the mountain. Limestone presents both advantages and problems. It is strong under compression but vulnerable to erosion, cracking, and water infiltration. Modern engineers conduct extensive geological testing before placing heavy structures on fractured limestone. Medieval builders lacked modern instruments, yet they somehow identified stable sections of bedrock capable of supporting massive defensive walls. Excavations have revealed areas where the natural rock appears intentionally modified. Builders cut, leveled, and shaped portions of the summit before construction. In some locations, walls appear locked directly into carved sections of bedrock, creating a unified structural system rather than separate architectural elements. The precision required for such work is remarkable. A poorly positioned wall could shift under its own weight, particularly during freeze-thaw cycles common in the Balkan climate. Winter temperatures often move above and below freezing, causing water trapped within rock fractures to expand and contract repeatedly. This process destroys many historical structures, yet significant portions of Srebrenik remain standing after more than 600 years. How medieval engineers evaluated geological stability without modern surveying equipment remains one of the fortress's greatest unanswered questions. Every fortress faces the same fundamental challenge: water. For a mountain fortress, the challenge becomes exponentially more difficult. Military historians estimate that a single person requires several liters of water daily for drinking and food preparation. Horses require significantly more. During prolonged sieges, access to water often determined whether a fortress survived or surrendered. Srebrenik's position creates a serious logistical puzzle. The fortress stands high above surrounding water sources, and transporting water manually would have been impractical during wartime. Archaeologists have identified cistern systems designed to collect rainwater, but debate continues regarding whether these reservoirs alone could support a large defensive garrison. Some researchers propose that sophisticated rainwater harvesting systems existed throughout the complex. Others suggest the possibility of deeper storage structures or now-lost supply mechanisms. Similar questions have emerged at mountain fortresses across Europe and the Middle East, where surviving remains often reveal only fragments of ancient hydraulic systems. The engineering challenge is enormous. A medieval garrison of merely 100 people could require hundreds of litres of water every day. Maintaining such supplies during a siege lasting weeks or months would demand careful planning, accurate calculations, and reliable storage infrastructure. The fact that Srebrenik functioned successfully as a fortress suggests that its builders solved this problem. The exact solution, however, remains uncertain. At first glance, Srebrenik appears irregular because it follows the natural shape of the mountain. Closer examination reveals something far more sophisticated. The walls, towers, gateways, and defensive positions were arranged to maximize visibility and defensive coverage. Approaching attackers would have been exposed to overlapping fields of fire from multiple directions. Blind spots were minimized despite the irregular terrain. Modern military architecture relies heavily on geometric calculations to optimize defensive positions. While medieval builders lacked digital modeling software, they clearly understood practical geometry. The fortress demonstrates careful consideration of elevation, angles of attack, visibility corridors, and defensive coordination. This is particularly impressive because Srebrenik's builders could not simply apply a standard design. Every wall had to adapt to a uniquely shaped rock formation. The result resembles a custom-engineered defensive machine integrated directly into the landscape. How medieval surveyors achieved such accuracy remains uncertain. They likely relied on ropes, measuring rods, plumb lines, sighting techniques, and accumulated practical knowledge. Yet, the level of optimization visible at the fortress suggests a degree of engineering expertise often underestimated in discussions of medieval technology. One of Srebrenik's most recognizable features is the bridge connecting the fortress to the surrounding terrain. Today, visitors cross a stone bridge, but historians suspect that the original defensive arrangement may have been significantly different. Many medieval fortresses employed wooden drawbridges, removable bridge sections, or complex gate systems designed to isolate the stronghold during attacks. If similar systems existed at Srebrenik, much of the evidence has disappeared. This creates an important archaeological problem. The visible fortress may represent only part of the original defensive network. Critical military technologies could have been constructed primarily from timber. It rarely survives for centuries. The result is a fortress whose most advanced defensive components may no longer exist. Researchers can study the stone structures, but the complete system remains partially hidden by time. Legends surrounding Srebrenik frequently mention secret tunnels, hidden passages, and underground chambers. Such stories are common among medieval fortresses, but they often originate from real architectural features. Many fortified sites incorporated escape routes, storage rooms, concealed corridors, and protected communication passages. Limited investigations at Srebrenik have identified cavities and structural spaces within the rock formation, yet comprehensive subsurface mapping remains incomplete. Modern technologies such as ground-penetrating radar, laser scanning, and three-dimensional geological modeling have transformed archaeological research. Nevertheless, large portions of the fortress's subsurface environment remain insufficiently explored. If additional underground structures exist, they could fundamentally change our understanding of how the fortress operated during wartime. They might reveal hidden storage systems, emergency exits, water infrastructure, or construction methods currently unknown. Hisar Hill is an archaeological site overlooking the modern city of Leskovac in southern Serbia. Hidden beneath its slopes is evidence of a technological mystery that challenges traditional views of European prehistory. Archaeologists have uncovered traces of metallurgy so advanced that some researchers believe the inhabitants may have mastered aspects of iron production centuries earlier than expected. The greatest mystery is not the metal itself, but how a prehistoric community developed furnaces, thermal control systems, and metallurgical knowledge that seem far more advanced than what historians once thought possible during the Late Bronze Age. The discovery of Hisar Hill began through archaeological investigations conducted during the 20th century, followed by extensive excavations that revealed multiple layers of occupation spanning thousands of years. Researchers uncovered fortifications, workshops, furnaces, slag deposits, and metal artifacts. What initially appeared to be a typical prehistoric settlement soon became one of the most controversial metallurgical sites in the Balkans. Scientific analyses suggested that some iron-related remains could date to between approximately 130 and 1100 BC, a period traditionally associated with the final centuries of the Bronze Age rather than established iron production. The first mystery concerns the unexpected appearance of iron technology. For generations, historians believed that large-scale iron metallurgy emerged in Anatolia and the Near East, before spreading gradually across Europe. After approximately 1200 BC, the traditional model placed the Balkans among the recipients of this technological revolution, rather than its innovators. However, excavations at Hisar Hill produced evidence that complicates this narrative. Researchers discovered iron objects and metallurgical residues associated with layers dating to the Late Bronze Age. If these dates accurately reflect local production rather than imported goods, then the inhabitants of Hisar may have been experimenting with iron at nearly the same time as some of the earliest iron-producing societies known anywhere in the world. This possibility creates a significant technological puzzle. Extracting iron from ore is fundamentally different from working copper or bronze. Copper melts at approximately 1085 degrees Celsius, while iron requires much higher temperatures and more complex chemical reactions. Ancient metallurgists could not simply place iron ore into a fire and wait for metal to emerge. They needed carefully designed furnaces, capable of maintaining temperatures exceeding 150 degrees Celsius while simultaneously controlling airflow and carbon monoxide concentrations. Modern metallurgists understand these processes through chemistry and thermodynamics. The people of Hisar possessed neither written scientific theories nor mathematical models, yet the evidence suggests they may have achieved similar practical results through observation and experimentation. The second and perhaps greatest mystery involves the furnace systems themselves. Archaeologists discovered evidence of metallurgical installations whose performance appears surprisingly sophisticated for their age. Excavations revealed furnace remains, slag accumulations, vitrified surfaces, and heat-altered clay, indicating prolonged exposure to extremely high temperatures. The distribution of these remains suggests organized production rather than occasional experimentation. Some furnaces appear to have been carefully positioned to maximize airflow, while the construction materials demonstrate an understanding of thermal resistance. Experimental archaeologists attempting to recreate prehistoric furnaces often encounter a major challenge. Maintaining temperatures above 150 degrees Celsius for extended periods requires an efficient supply of oxygen. Even small interruptions in airflow can cause temperatures to fall rapidly, ruining the reduction process. Modern reconstructions frequently rely on multiple workers operating bellows continuously. Yet the furnace remains at Hisar indicate a level of consistency that would have required remarkable operational discipline. Some researchers have proposed that the inhabitants developed highly effective airflow management systems that remain only partially understood today. The furnace linings create another mystery. Analyses of surviving clay fragments indicate repeated exposure to intense thermal stress. Under such conditions, ordinary clay tends to crack, deform, or collapse. The builders at Hisar appear to have selected and prepared refractory materials capable of surviving repeated heating cycles. Similar challenges confronted much later iron-producing civilizations. Medieval European bloomery furnaces, for example, required constant maintenance because furnace walls deteriorated rapidly. The fact that prehistoric metallurgists may have achieved comparable durability raises important questions about their material knowledge. Comparisons with other ancient metallurgical centers make the puzzle even more intriguing. At sites associated with the Hittites in Anatolia, iron production emerged within highly organized societies possessing extensive trade networks and specialized crafts. In contrast, Hisar was a hilltop settlement far from the great urban centers of the eastern Mediterranean. Yet some of its metallurgical evidence suggests technical capabilities approaching those found in regions traditionally considered more advanced. This does not necessarily mean Hisar surpassed the Hittites. Rather, it suggests that technological innovation may have been more geographically widespread than historians once assumed. The third mystery concerns production efficiency. Slag recovered from Hisar contains valuable clues about ancient metallurgical processes. Modern microscopic and chemical analyses reveal how effectively ancient workers separated metal from waste material. Some samples indicate surprisingly efficient extraction rates. Achieving such results requires precise control of temperature, fuel quality, furnace design, and ore preparation. Even slight errors can dramatically reduce metal yield. The consistency observed in some metallurgical residues suggests that the process was not based on random trial and error alone. Instead, knowledge may have been accumulated across generations through systematic observation and transmission. Another mystery involves fuel consumption. Producing iron requires enormous quantities of charcoal. Experimental studies demonstrate that ancient bloomery furnaces often consumed several kilograms of charcoal for every kilogram of usable metal produced. This creates a logistical challenge. A community engaged in sustained metallurgical activity would need access to large forest resources and organized systems for charcoal production. Archaeologists have identified evidence of extensive woodland exploitation throughout parts of prehistoric Europe, but the precise scale of resource management at Hisar remains uncertain. If iron production occurred regularly, the settlement may have required economic and organizational structures more complex than previously imagined. The fourth mystery concerns trade networks. Chemical analyses of certain artifacts suggest that not all raw materials originated locally. Some metallic compositions differ from nearby ore sources, raising the possibility of long-distance exchange. During the Late Bronze Age, the Balkans formed part of a vast network connecting Central Europe, the Aegean, Anatolia, and the Black Sea region. Copper, tin, amber, gold, and luxury goods moved across enormous distances. Hisar may have occupied a strategic position within these networks. If so, technological knowledge may have traveled alongside physical materials. The movement of metallurgical expertise across prehistoric Europe remains one of archaeology's least understood phenomena. The fifth mystery concerns social organization. Metallurgy is not merely a technical activity. It requires specialists, laborers, resource procurement systems, and knowledge transmission mechanisms. The furnace remains suggest repeated production episodes rather than isolated experiments. Such continuity implies the existence of trained craftsmen capable of preserving and teaching complex procedures. Yet, no written records survive. Every aspect of furnace construction, ore selection, charcoal preparation, and metalworking would have depended entirely on human memory and apprenticeship. The survival of such knowledge across generations remains one of the most remarkable achievements of prehistoric societies. The sixth mystery involves the settlement's defensive position. Hisar occupies a commanding hill overlooking surrounding valleys. Archaeological evidence indicates fortifications and strategic planning. This combination of defense and metallurgy raises an important question. Was the site simply a settlement with metalworking activities, or was it a specialized center whose economic importance justified substantial protection? Throughout history, access to metal production often translated into military and political power. Communities capable of producing superior tools and weapons enjoyed significant advantages over their neighbors. Hisar's elevated location may reflect the strategic value of its technological capabilities. Židovar is an ancient hilltop settlement in eastern Serbia, overlooking the Karaš River valley near the modern border with Romania. What archaeologists discovered here challenges a long-standing assumption about Iron Age Europe, that technological sophistication belonged only to great civilizations. Hidden beneath a small plateau less than 1 hectare in size lies evidence of engineering, metallurgy, and trade systems whose complexity remains only partially understood. The discovery of Židovar began through archaeological investigations conducted throughout the 20th century. Excavations revealed multiple layers of occupation dating from the Bronze Age through the Late Iron Age and into the Roman period. What initially appeared to be a typical fortified settlement soon produced something extraordinary, evidence that a relatively small community possessed access to advanced silverworking technologies, extensive trade networks, and engineering capabilities comparable to much larger centers. The greatest mystery of Židovar is not the settlement itself. The greatest mystery is how such a small community achieved a level of technological sophistication that seems disproportionate to its size. One of the first mysteries concerns the strategic location of the settlement. Židovar occupies a naturally elevated plateau rising approximately 40 meters above the surrounding landscape. From this position, inhabitants could observe movement across important routes linking the Danube Basin, the Carpathian Mountains, and the Pannonian Plain. Archaeologists have long recognized that controlling trade routes often created wealth, but Židovar appears unusually well positioned. The settlement occupies what could be described as a natural surveillance platform. The question is how Iron Age communities identified locations with such remarkable strategic value. Modern military planners rely on topographic maps, aerial photography, and satellite imagery. The inhabitants of Židovar possessed none of these tools, yet their choice resembles the location selection strategies later employed by Roman military engineers. Some researchers believe the settlement formed part of a wider communication and observation network stretching across southeastern Europe. If true, it suggests a level of regional coordination that remains poorly understood. The second and perhaps most fascinating mystery involves silver technology. Among the most important discoveries at Židovar was a treasure containing silver jewelry, decorative objects, and luxury goods. At first glance, these artifacts appear similar to elite ornaments found throughout Iron Age Europe. Detailed examination, however, revealed manufacturing techniques that continue to surprise specialists. Several silver objects exhibit evidence of filigree work. Filigree involves twisting extremely thin metal wires and arranging them into highly detailed decorative patterns. Even today, producing fine filigree requires specialized tools, precise temperature control, and considerable skill. Some of the wires discovered at Židovar measure fractions of a millimeter in thickness. More remarkable is the presence of granulation technology. Granulation involves attaching tiny metallic spheres onto a metal surface to create intricate geometric designs. Individual granules can be less than 1 millimeter in diameter. The process demands precise control over heat because temperatures must be high, enough to fuse the particles without melting the entire object. This presents a major archaeological puzzle. Modern metallurgical analysis indicates that silver melts at approximately 961 degrees Celsius. Successful granulation requires craftsmen to operate within an extremely narrow thermal range. Too little heat prevents bonding, while too much heat destroys the design. Yet the artisans of Jidavar achieve this repeatedly. The mystery is not that they produced jewellery. The mystery is that they achieved levels of precision approaching those seen in famous Mediterranean workshops associated with Greek, Hellenistic, and Roman elites. Comparisons become even more intriguing when examined scientifically. Experimental archaeologists attempting to reproduce ancient granulation techniques frequently require carefully controlled furnaces and repeated trials. Some modern reconstructions have shown failure rates exceeding 30% during training phases. Yet artifacts from Jidavar demonstrate consistent craftsmanship across multiple objects. This raises an important question. Where did this knowledge originate? No complete workshop has been discovered, no detailed manufacturing instructions survive, and no written records explain the production process. Archaeologists can analyze the finished products, but the technological chain connecting raw silver ore to completed jewellery remains largely invisible. The source of the silver itself raises additional questions. Chemical studies suggest that some materials may have originated hundreds of kilometers away. If true, craftsmen at Jidavar had access not only to advanced metallurgical knowledge, but also to long-distance supply networks capable of transporting valuable resources across politically fragmented territories. This creates an economic mystery. Advanced silver production requires miners, traders, metal refiners, artisans, and wealthy customers. Such systems usually emerge within large urban centres. Jidavar was not a large city. The settlement covered less than 1 hectare, making it dramatically smaller than many contemporary regional centres. How such a modest community supported sophisticated luxury production remains unclear. A third mystery concerns trade connections extending across vast distances. Archaeologists discovered materials that did not originate locally, including amber and imported luxury goods. Amber is particularly significant because major prehistoric sources are concentrated near the Baltic region, the more than 1,000 kilometers from Jidavar. To understand the scale of this network, consider the logistics involved. Transporting valuable goods over such distances required secure routes, trusted intermediaries, and stable exchange systems. Unlike modern commerce, these transactions occurred without centralized governments, modern banking, or advanced transportation infrastructure. Yet imported materials continued arriving. The evidence suggests that Jidavar participated in exchange networks connecting Central Europe, the Balkans, and regions influenced by the Roman world. Such networks resemble economic arteries distributing resources across enormous geographic areas. The exact mechanisms that sustain these systems remain one of the unresolved questions of Iron Age archaeology. The fourth mystery involves the settlement's defensive engineering. Excavations have revealed evidence of fortifications, earthworks, and defensive structures designed to protect the plateau. Although not as massive as the walls of major ancient cities, these defences demonstrate careful planning. Engineers exploited natural topography to maximise protection while minimising construction effort. This reflects a sophisticated understanding of terrain analysis. Military architects throughout history have emphasised the importance of combining artificial defences with natural obstacles. The builders of Jidavar appear to have applied exactly this principle centuries before formal military engineering manuals existed. Researchers still debate whether the settlement functioned primarily as a fortress, a trading centre, a regional administrative hub, or a combination of all three. The fifth mystery concerns cultural identity. Artifacts recovered from the site display influences associated with Celtic groups, Dacian populations, and neighbouring communities. Rather than fitting neatly into a single cultural category, Jidavar appears to represent a crossroads where technologies, artistic traditions, and economic practices converged. This blending complicates interpretation. Were technological innovations imported from elsewhere? Were they developed locally? Or did they emerge through continuous interaction between multiple cultures? No definitive answer exists. Finally, there is the mystery of disappearance. By the 1st century AD, the settlement gradually lost its importance. Archaeologists have found no clear evidence of catastrophic destruction. No massive battle appears responsible, and no natural disaster explains the decline. Instead, Židava seems to have faded quietly from history. The disappearance is particularly puzzling because technological knowledge does not simply vanish. Communities capable of advanced silverworking, regional trade coordination, and strategic engineering normally leave stronger historical footprints. Yet much of Židava's story remains hidden,